Tonight, we begin with something quietly miraculous happening above your head right now. Invisible rivers of water vapor drift through the atmosphere, carrying the promise of rain to places thousands of miles away from where they first began their journey. The title of our exploration might suggest that rain makes conscious choices, but the truth is far more elegant. Rain doesn't decide anything at all. Instead, it follows the ancient laws of physics with a precision so perfect, so predictable, that we can trace every droplet back to its origins and forward to its destination. Picture this moment. As you listen to these words, water molecules that once danced in distant oceans are condensing into clouds somewhere above you. Others are already beginning their descent, pulled by gravity toward the earth below. This isn't chance or randomness. It's the result of forces so fundamental, so quietly powerful, that they've been shaping our planet's climate for billions of years. The story of how rain finds its way to your window begins not in the clouds, but in the vast blue expanses of our oceans. Here, under the gentle warmth of sunlight, lies the engine that drives all weather on Earth. The ocean holds 97% of all water on our planet. Think about that for a moment. Nearly every drop of water that has ever fallen as rain, every snowflake that has ever touched your skin, every stream that has ever carved a valley, it all began here, in these deep blue reservoirs that cover most of our world. But water doesn't simply leap from ocean to sky. The process is far more subtle, more graceful than that. Energy from the sun strikes the ocean surface, and individual water molecules begin to move faster, vibrate with increasing intensity. When they gain enough energy, they break free from their liquid bonds and rise invisibly into the air as water vapor. This is evaporation, and it happens continuously, quietly, all around us. Every second, millions of gallons of water transform from liquid to gas, beginning journeys that might take them across continents before they return to Earth again. The numbers are staggering, yet peaceful in their enormity. Each year, our oceans release approximately 434,000 cubic kilometers of water into the atmosphere. To put this in perspective, imagine every river on Earth flowing for an entire year. That volume wouldn't even come close to what evaporates from our oceans in the same time. This constant, gentle lifting of moisture creates the raw material for every cloud, every storm, every gentle spring shower. Yet evaporation isn't limited to the oceans. Lakes contribute their share, their surfaces shimmering as water molecules escape into the warming air. Rivers add to the atmospheric moisture as they flow toward the sea. Even the soil beneath your feet releases water vapor through a process called evapotranspiration, where plants draw water from the ground and release it through their leaves. Every leaf, every blade of grass, every tree in the forest acts as a tiny pump, pulling water up from below and sending it skyward. The air around us becomes a vast, invisible reservoir. At any given moment, the atmosphere contains about 12,900 cubic kilometers of water in vapor form. This might sound like an enormous amount, but it represents less than 1% of all the water on Earth. Yet this tiny fraction drives all our weather, creates all our precipitation, sustains all life on land. It's a delicate balance, maintained by forces that operate on scales both cosmic and molecular. Temperature plays the conductor in this atmospheric orchestra. Warm air can hold far more water vapor than cold air. For every degree Celsius that air temperature rises, the atmosphere can accommodate about 7% more moisture. This fundamental relationship, described by the Clausius-Clapeyron equation, governs where and when water vapor will condense back into liquid form. Near the equator, where tropical sun beats down on warm oceans, the air becomes saturated with moisture. These warm, humid air masses rise naturally, carrying vast quantities of water vapor high into the atmosphere. As they ascend, they encounter cooler temperatures, and their capacity to hold moisture begins to diminish. This is where the magic happens, where invisible vapor begins its transformation back into visible clouds, and, eventually, rain. But cooling air alone isn't enough to create precipitation. The atmosphere needs something else, tiny particles so small they're measured in micrometers. These are called condensation nuclei, and they're everywhere around us. Salt crystals from ocean spray, dust particles lifted from distant deserts, pollen grains from forests, even microscopic debris from meteors burning up in the upper atmosphere. These particles provide surfaces where water vapor can begin to condense. The process starts small. A single water molecule encounters a condensation nucleus and adheres to it. Then another molecule joins, and another. Gradually, microscopically, a droplet begins to form. In the cold upper atmosphere, these droplets might freeze instead, creating tiny ice crystals. Whether liquid or solid, these microscopic particles are the seeds of every cloud. Individual droplets and ice crystals remain invisible to the naked eye, but when billions of them cluster together, they create the familiar white and grey formations we call clouds. Each cloud is essentially a visible collection of countless tiny water droplets or ice crystals suspended in air, waiting for the right conditions to begin their journey back to Earth. Not every cloud produces rain. In fact, most don't. For precipitation to occur, the tiny droplets or ice crystals must grow large enough and heavy enough to overcome the upward air currents that keep them suspended. This growth happens through collision and coalescence. Larger droplets fall faster than smaller ones, collecting their tinier neighbors as they descend. Ice crystals can grow by capturing water vapor directly from the surrounding air, or by colliding with supercooled water droplets that freeze instantly upon contact. The size requirements are specific and unforgiving. A typical cloud droplet measures about 10 micrometers across, roughly 1/10 the width of a human hair. A raindrop, by contrast, ranges from 500 micrometers to several millimeters in diameter. For a cloud droplet to become large enough to fall as rain, it must grow to at least 50 times its original size. This transformation requires time, the right atmospheric conditions, and often a complex interplay of physical processes occurring simultaneously at different levels within the cloud. Atmospheric pressure adds another layer of complexity to this delicate dance. Air pressure varies with altitude, temperature, and weather patterns. High-pressure systems generally suppress cloud formation by pushing air downward, preventing the upward motion necessary for condensation. Low-pressure systems do the opposite, encouraging air to rise, cool, and form clouds. The boundaries between these pressure systems create fronts, regions where different air masses meet and interact. When a warm, moist air mass encounters a cooler, denser air mass, the warm air is forced upward along the sloping boundary between them. As it rises, it cools, and its moisture begins to condense. This process can create extensive cloud systems stretching for hundreds of kilometers, capable of producing steady, widespread precipitation across vast regions. The three-dimensional structure of these atmospheric interactions defies simple explanation. Air masses don't simply slide past each other like layers in a cake. They mix, spiral, and interact in complex patterns influenced by the Earth's rotation, the heating and cooling of land and sea, the presence of mountains and valleys, and countless other factors. Weather fronts can be thousands of kilometers long, but only a few kilometers thick, creating narrow bands where most of the precipitation occurs. Wind patterns add yet another dimension to the story of where rain falls. The atmosphere is never still. Global circulation patterns, driven by the uneven heating of Earth's surface, create prevailing winds that carry moisture-laden air masses across continents and oceans. The trade winds near the equator, the westerlies in the mid-latitudes, the polar easterlies near the poles, all contribute to the global redistribution of water vapor. These large-scale wind patterns interact with local topography in ways that dramatically influence precipitation. When moist air encounters a mountain range, it's forced upward along the windward slopes. As it rises, it cools, and its moisture condenses into clouds and precipitation. This orographic lifting can produce some of the heaviest rainfall on Earth. The windward slopes of mountains often receive several times more precipitation than the surrounding lowlands. Mount Wailea on the Hawaiian island of Kauai exemplifies this process perfectly. Despite lying in a region that typically receives only modest rainfall, this mountain peak captures moisture from the trade winds and transforms it into precipitation. Annual rainfall here can exceed 10,000 millimeters, making it one of the wettest spots on Earth. Yet just a few dozen kilometers away, in the rain shadow on the leeward side of the mountains, some areas receive less than 500 millimeters of rain per year. This rain shadow effect occurs when air masses, having dropped most of their moisture on the windward side of mountains, descend the leeward slopes. As descending air warms and expands, its capacity to hold moisture increases, creating dry conditions. The western United States provides numerous examples of this phenomenon, where lush green coastal ranges give way to arid deserts just inland. The timing of precipitation depends on atmospheric stability and instability. Stable air resists vertical motion, leading to calm weather and few clouds. Unstable air encourages vertical motion, creating conditions favorable for cloud development and precipitation. The degree of instability depends on how temperature changes with altitude. In an unstable atmosphere, air that begins to rise will continue rising because it remains warmer and less dense than the surrounding air. Convective precipitation occurs when surface heating creates pockets of unstable air that rise rapidly, forming towering cumulus and cumulonimbus clouds. These convective systems can produce intense, localized rainfall, sometimes dropping several centimeters of rain in just a few hours. The precipitation from these systems tends to be sporadic and geographically limited, which explains why one neighborhood might experience a torrential downpour while another, just a few kilometers away, remains completely dry. The formation of these convective systems follows patterns as reliable as clockwork, yet each storm carries its own unique fingerprint. When morning sunlight begins to warm the Earth's surface, it doesn't heat everything equally. Dark soil absorbs more energy than light-colored sand. Urban concrete and asphalt become significantly warmer than surrounding forests or grasslands. Bodies of water heat up more slowly than land, creating temperature contrasts that set the stage for atmospheric motion. These temperature differences create what meteorologists call thermal gradients, invisible boundaries, where warm air meets cooler air. The warm air, being less dense, begins to rise in gentle columns called thermals. If you've ever watched a hawk circling effortlessly without flapping its wings, you've observed a bird riding one of these invisible elevators of rising warm air. As these thermals ascend, they carry moisture with them. The higher they rise, the cooler the surrounding air becomes. Eventually, the rising air reaches a level where it can no longer hold all its moisture in vapor form. This critical altitude is called the condensation level, and it's where visible clouds begin to form. The process resembles a slow-motion explosion of cotton, billowing upward and outward as more warm air feeds the growing cloud from below. These cumulus clouds, with their characteristic puffy rounded tops and relatively flat bases, mark the visible boundary where invisible water vapor transforms into countless tiny droplets. But not every cumulus cloud grows into a rain-producing system. For precipitation to develop, the cloud must continue growing vertically, reaching heights where temperatures drop well below freezing. Only then can the complex processes of droplet collision and ice crystal formation create particles large enough to fall as rain. The atmosphere has its own rhythm, its own breathing pattern that influences where and when these convective systems develop. During stable atmospheric conditions, rising air encounters layers of warmer air aloft that act like invisible ceilings, preventing clouds from growing tall enough to produce precipitation. These temperature inversions, as they're called, create those perfectly clear days when puffy white clouds dot the sky but never threaten rain. When atmospheric conditions become unstable, however, the situation changes dramatically. Rising air parcels find that they remain warmer than their surroundings, even at great heights, allowing them to continue ascending. These conditions can produce towering cumulonimbus clouds that reach altitudes of 15,000 meters or more, their anvil-shaped tops spreading out as they encounter the stable stratosphere above. The internal structure of these massive clouds resembles a vertical conveyor belt of immense proportions. Warm, moist air rushes upward through the core of the cloud at speeds that can exceed 30 meters per second. Near the top, this air spreads outward and begins to descend along the cloud's edges, creating a circulation pattern that can persist for hours. Within this vertical circulation, water droplets and ice crystals undergo constant collisions and transformations. Small droplets merge into larger ones through a process called collision and coalescence. Ice crystals grow by capturing water vapor directly from the air around them, or by colliding with supercooled water droplets that freeze instantly upon contact. The size and weight of these growing precipitation particles determine their eventual fate. Tiny droplets remain suspended in the air indefinitely, contributing to the cloud's visible structure but never falling to Earth. Medium-sized droplets may begin to fall, only to evaporate before reaching the ground in a phenomenon called virga. Only the largest, heaviest particles successfully complete the journey from cloud to surface as precipitation. Temperature variations within the cloud create different types of precipitation. If the entire column of air from cloud to ground remains above freezing, water droplets fall as rain. If they encounter a layer of freezing air, they become sleet. If the freezing layer extends all the way to the ground, precipitation falls as snow. These vertical temperature profiles explain why different types of precipitation can occur simultaneously in nearby locations. The geographical distribution of convective precipitation follows patterns influenced by local topography and land use. Urban areas, with their abundance of heat-absorbing surfaces, often experience more frequent afternoon thunderstorms than surrounding rural areas. This urban heat island effect can increase local precipitation by 10 to 15%, creating microclimates where rain falls more frequently on cities than on the countryside that surrounds them. Coastal regions experience their own unique precipitation patterns, driven by the temperature contrast between land and sea. During the day, land surfaces warm faster than ocean water, creating onshore breezes that carry moisture inland. This moisture often encounters the rising warm air over land, contributing to afternoon and evening precipitation along coastal areas. As night falls and land surfaces cool more rapidly than the ocean, the process reverses. Offshore breezes carry moisture back toward the sea, and precipitation patterns shift accordingly. These daily cycles create predictable timing for coastal precipitation, with many regions experiencing peak rainfall during specific hours of the day. The seasonal migration of global weather patterns adds another layer of predictability to precipitation distribution. The intertropical convergence zone, a band of low pressure that encircles the Earth near the equator, shifts northward and southward with the changing seasons. This movement brings wet and dry periods to different regions in a pattern that has remained consistent for thousands of years. Monsoon systems represent the most dramatic example of seasonal precipitation patterns. These massive atmospheric circulation systems develop when continents heat up during summer months, creating powerful low-pressure areas that draw moist air from adjacent oceans. The resulting precipitation can account for 80% or more of a region's annual rainfall, delivered in just a few months of intense weather activity. The physics governing monsoon development operates on a continental scale involving the differential heating of land masses and oceans across entire hemispheres. During winter, continents cool more rapidly than oceans, reversing the pressure patterns and creating the dry phase of the monsoon cycle. This seasonal rhythm affects the lives of billions of people, determining agricultural cycles and water availability across vast regions of Asia, Africa, and Australia. Mountain ranges play a fundamental role in shaping these large-scale precipitation patterns. The Himalayas, stretching across southern Asia, act as a massive barrier that forces moisture-laden monsoon winds upward, creating some of the heaviest rainfall on Earth along their southern slopes. The town of Cherrapunji in northeastern India receives an average of 11,000 millimeters of rain annually, nearly all of it during the summer monsoon season. This orographic enhancement of precipitation operates through principles as reliable as gravity itself. When air encounters a mountain slope, it has no choice but to rise. As it ascends, it expands and cools due to decreasing atmospheric pressure. This cooling reduces the air's capacity to hold moisture, forcing excess water vapor to condense into clouds and precipitation. The mathematical relationship between altitude and temperature change is remarkably consistent. For every 1,000 meters of elevation gained, air temperature typically decreases by about 6.5 degrees Celsius. This environmental lapse rate, as meteorologists call it, allows precise predictions of where condensation will begin and precipitation will form. The windward side of mountain ranges captures the vast majority of available moisture, leaving the leeward side in what meteorologists term a rain shadow. Air that has deposited its moisture while crossing the mountains descends the opposite slopes, warming and drying as it loses altitude. This descending air can become significantly warmer and drier than it was before encountering the mountain, creating desert conditions, even in regions that might otherwise support lush vegetation. The western coast of North America provides a textbook example of these orographic effects. Moist air from the Pacific Ocean encounters the Coast Range, the Cascades, and the Sierra Nevada in succession. Each mountain range extracts moisture from the air, leaving progressively less water vapor available for the ranges further inland. Seattle, positioned on the windward side of the Cascade Range, receives about 950 millimeters of precipitation annually. Spokane, located just 300 kilometers to the east, but on the leeward side of the same mountains, receives less than 400 millimeters per year. This dramatic difference occurs despite the relatively short distance separating these two cities. The Rocky Mountains create an even more pronounced rain shadow effect. Denver, situated on the eastern edge of the Rockies, receives about 400 millimeters of precipitation annually. Cities further east, away from the mountain's influence, typically receive significantly more rainfall. This pattern extends across the entire western United States, where mountain ranges create a complex mosaic of wet and dry regions determined entirely by topography and prevailing wind patterns. Atmospheric rivers represent another mechanism by which moisture travels vast distances before condensing into precipitation. These narrow corridors of concentrated water vapor, typically a few hundred kilometers wide but thousands of kilometers long, transport moisture from tropical and subtropical oceans toward higher latitudes. A single atmospheric river can carry more water vapor than the Amazon River transports in liquid form. When these moisture-laden air masses encounter coastal mountain ranges, they can produce extreme precipitation events, sometimes delivering a month's worth of rain in just a few days. The Pacific coast of North America experiences regular visits from atmospheric rivers originating in the tropical Pacific. These events, sometimes called Pineapple Express storms when they originate near Hawaii, can bring both beneficial water supplies and destructive flooding to California and the Pacific Northwest. The formation and movement of atmospheric rivers depend on large-scale pressure patterns across entire ocean basins. High-pressure areas act as barriers that deflect these moisture streams, while low-pressure systems can intensify and focus them. The precise track of an atmospheric river determines which coastal regions receive heavy precipitation and which remain dry. Climate oscillations add yet another layer of variability to global precipitation patterns. The El Niño Southern Oscillation, a periodic warming and cooling of tropical Pacific waters, influences weather patterns across the entire globe. During El Niño events, when Pacific waters warm, storm tracks shift northward along the western coast of the Americas, bringing increased precipitation to California and the southern United States, while reducing rainfall in Australia and Southeast Asia. La Niña events produce the opposite effect, cooling Pacific waters and shifting storm tracks southward. These oscillations occur irregularly, typically every 2 to 7 years, and can persist for months or even years. Their influence extends far beyond the Pacific Basin, affecting monsoon patterns in India, hurricane activity in the Atlantic, and drought conditions across Africa. The North Atlantic Oscillation represents another major climate pattern that influences precipitation across Europe and eastern North America. This oscillation involves changes in the pressure difference between Iceland and the Azores, which affects the strength and position of the jet stream. When the oscillation is in its positive phase, the jet stream remains strong and follows a relatively straight path, directing storms toward northern Europe, while keeping them away from the Mediterranean region. During negative phases of the North Atlantic Oscillation, the jet stream weakens and becomes more meandering, allowing storms to reach southern Europe while blocking them from northern regions. These changes can reverse typical precipitation patterns, bringing drought to normally wet regions and unexpected rainfall to typically dry areas. The Arctic Oscillation operates on an even larger scale, involving pressure changes across the entire Arctic region. This oscillation influences the position of the polar jet stream, which acts as a boundary between cold Arctic air and warmer air from lower latitudes. When the oscillation is positive, the jet stream remains tightly wound around the Arctic, keeping cold air confined to high latitudes. When it becomes negative, the jet stream becomes more wavy and unstable, allowing Arctic air to plunge southward into lower latitudes, while simultaneously allowing warm air to penetrate northward. These large-scale climate oscillations demonstrate how precipitation patterns in one region can be connected to atmospheric conditions thousands of kilometers away. A warming ocean surface near Peru can influence rainfall patterns in India. Pressure changes in the Arctic can affect storm tracks across North America and Europe. The atmosphere operates as a single, interconnected system where changes in one region propagate around the globe through complex feedback mechanisms. Ocean currents add another dimension to these global connections. The Gulf Stream, carrying warm water northward along the eastern coast of North America, moderates temperatures across the North Atlantic region and influences precipitation patterns from Florida to Norway. When this current strengthens or weakens, it affects evaporation rates, atmospheric moisture content, and storm development across a vast area. The thermohaline circulation, often called the global conveyor belt, transports heat and moisture around the world's oceans in a cycle that takes roughly 1,000 years to complete. This slow but massive circulation pattern influences long-term climate patterns and precipitation distribution across entire continents. Changes in ocean temperature and salinity can alter these circulation patterns, leading to shifts in precipitation that persist for decades or centuries. The medieval warm period and the Little Ice Age, Both involved changes in ocean circulation that affected rainfall patterns across Europe, Asia, and the Americas. Human activities have begun to influence these natural precipitation patterns in measurable ways. Urban development creates heat islands that enhance local convection and precipitation. Agriculture alters evapotranspiration rates across vast areas. Deforestation changes surface roughness and moisture availability. Irrigation transfers water from rivers and aquifers to the atmosphere through evaporation. The warming climate is intensifying the global water cycle, increasing evaporation rates and atmospheric moisture content. For every degree of warming, the atmosphere can hold approximately 7% more water vapor. This additional moisture doesn't distribute evenly around the globe, but tends to concentrate precipitation in already wet regions, while making dry regions even drier. Storm systems in a warmer climate can access more atmospheric moisture, potentially producing more intense precipitation events. This explains why many regions are experiencing both more severe droughts and more extreme flooding as the climate changes. The same atmospheric patterns that once produced moderate precipitation now have access to more moisture, leading to more extreme outcomes. The measurement and prediction of precipitation have evolved from simple rain gauges to sophisticated networks of ground-based instruments, weather balloons, and satellites. Doppler radar can detect precipitation formation within clouds and track its movement across the landscape. Satellites monitor atmospheric moisture content and temperature profiles across the entire globe. Computer models now simulate the global atmosphere with remarkable detail, dividing the Earth into millions of grid cells and calculating the physical processes occurring within each cell. These models can predict precipitation patterns days or even weeks in advance, though accuracy decreases with time as small uncertainties grow into larger errors. Weather forecasting represents one of humanity's most successful applications of physics and mathematics to practical problems. The same equations that govern the behavior of individual air molecules also describe the movement of massive weather systems. By solving these equations numerically, meteorologists can predict where rain will fall with accuracy that would have seemed magical just a few decades ago. Despite these technological advances, precipitation prediction remains challenging because the atmosphere is a chaotic system where small changes can have large consequences. A temperature difference of just 1 degree or a pressure change of a few millibars can alter storm tracks and precipitation patterns over hundreds of kilometers. This sensitivity to initial conditions explains why weather forecasts become less reliable beyond about a week. Even perfect models with perfect input data would eventually lose accuracy as tiny uncertainties amplify over time. This fundamental limitation, known as the butterfly effect, places theoretical limits on long-term weather prediction. However, climate prediction operates on different principles than weather forecasting. While we cannot predict the weather on a specific day months in advance, we can predict seasonal and annual precipitation patterns with considerable skill. Climate models focus on long-term averages rather than day-to-day variations, making them less sensitive to small initial uncertainties. Seasonal forecasts can predict whether a region is likely to experience above normal or below normal precipitation months in advance. These forecasts prove valuable for agriculture, water management, and disaster preparedness, even though they cannot specify exactly when rain will fall. The physics of precipitation connects the molecular scale to the planetary scale in a continuous chain of cause and effect. Individual water molecules evaporating from ocean surfaces eventually influence continental weather patterns. Local temperature differences create global circulation systems. Microscopic cloud condensation nuclei determine the formation of storms visible from space. This interconnectedness reveals precipitation as part of a larger system that redistributes energy and moisture around the planet. Every raindrop that falls represents the endpoint of a journey that began with solar energy warming distant oceans, continued through complex atmospheric processes, and ended with gravity pulling that transformed moisture back to Earth. The elegance of this system lies not in conscious decision-making, but in the inevitable unfolding of physical laws. Rain follows the path of least resistance, condensing where conditions favor condensation, falling where gravity overcomes atmospheric support. What appears as randomness or choice is actually the deterministic result of countless physical processes operating simultaneously across multiple scales of space and time. In quiet moments when rain patters against windows or drums gently on rooftops, we witness the culmination of processes that span the globe and connect every part of our planet's climate system. The water falling outside began its current journey in distant oceans, traveled invisible highways through the atmosphere, and now returns to Earth to begin the cycle anew. This ancient rhythm continues day and night, season after season, connecting all life on Earth through the gentle, persistent circulation of water between sea and sky, and back again, to back again. The delicate balance of atmospheric moisture reveals itself through patterns that have remained constant for millions of years, yet each day brings subtle variations that make every weather event unique. Understanding these patterns requires us to think in 4 dimensions, considering not just the horizontal movement of air masses across continents and oceans, but also their vertical motion through different layers of the atmosphere, all changing continuously through time. The atmosphere consists of distinct layers, each with its own characteristics and role in precipitation formation. The troposphere, where all our weather occurs, extends from the Earth's surface to an altitude of about 10 to 15 kilometers, depending on latitude and season. Within this relatively thin shell of air, temperature generally decreases with altitude, creating the conditions necessary for cloud formation and precipitation. But the atmosphere doesn't exist in isolation. It interacts constantly with the Earth's surface, drawing energy from sun-warmed land and sea, responding to the planet's rotation, and adapting to the changing seasons. These interactions create a complex web of feedback mechanisms that determine where moisture will condense and where rain will fall. Solar radiation provides the fundamental energy that drives all atmospheric motion. The sun's energy doesn't heat the Earth's surface evenly. Tropical regions receive more direct sunlight than polar areas, creating temperature gradients that span the entire globe. These gradients establish pressure differences that set air masses in motion, creating the winds that transport moisture from one region to another. The Earth's rotation adds a subtle but crucial influence to these air movements through what scientists call the Coriolis effect. This apparent force, caused by our planet's spin, deflects moving air masses to the right in the northern hemisphere and to the left in the southern hemisphere. Without this deflection, air would flow directly from high-pressure areas to low-pressure areas. Instead, it curves, creating the spiral patterns we see in weather systems and the meandering paths of jet streams. Jet streams represent rivers of fast-moving air that flow through the upper troposphere, typically at altitudes between 9 and 12 kilometers. These narrow bands of strong winds, often reaching speeds of over 200 kilometers per hour, act as steering currents for weather systems. They separate air masses of different temperatures and guide the movement of storms across continents. The position and strength of jet streams vary seasonally and can shift dramatically over periods of days or weeks. When jet streams follow relatively straight paths, they efficiently separate warm and cold air masses, leading to stable weather patterns. When they become more sinuous and develop large loops, they can transport Arctic air far southward or tropical air far northward, creating unexpected weather conditions in regions unaccustomed to such extremes. The interaction between jet streams and surface weather systems creates much of the day-to-day variability in precipitation patterns. A small shift in jet stream position can redirect storm tracks by hundreds of kilometers, bringing rain to regions that might otherwise remain dry while leaving typically wet areas in drought conditions. Surface features influence these atmospheric patterns in ways that persist across seasons and years. Large bodies of water moderate temperature fluctuations, creating more stable atmospheric conditions. Land masses, particularly continents, experience greater temperature extremes, leading to more variable weather patterns. The specific heat capacity of water means that oceans warm and cool much more slowly than land surfaces. During summer, continents become significantly warmer than adjacent seas, creating thermal low-pressure areas that draw moist air inland. During winter, the situation reverses, with relatively warm oceans creating conditions that favor storm development along coastlines. These seasonal temperature contrasts drive some of the world's most important precipitation patterns. The Asian monsoon system, which affects billions of people, develops when the Tibetan Plateau and surrounding land areas heat up during summer months. This heating creates a massive low-pressure area that draws moisture-laden air from the Indian Ocean, producing the heavy rains that sustain agriculture across much of South and Southeast Asia. The strength and timing of monsoon systems vary from year to year, influenced by ocean temperatures, snow cover on the Tibetan Plateau, and atmospheric circulation patterns across the Pacific and Indian Oceans. These variations can mean the difference between abundant harvests and widespread drought, demonstrating how large-scale atmospheric processes directly affect human societies. Similar processes operate on smaller scales throughout the world. Mediterranean climates, found along the western coasts of continents between roughly 30 and 40 degrees latitude, experience wet winters and dry summers due to the seasonal migration of storm tracks. During winter, these regions lie in the path of storms driven by the jet stream. During summer, high-pressure systems dominate, deflecting storms to higher latitudes. The predictability of these seasonal patterns allowed ancient civilizations to develop agriculture and plan their activities around expected rainfall. Even today, farmers and water managers rely on the general reliability of seasonal precipitation patterns, though climate change is beginning to alter some of these long-established cycles. Topographic features create their own microclimates and precipitation patterns that can vary dramatically over short distances. Valleys can channel moist air masses, concentrating precipitation in narrow bands. Hilltops and ridges can trigger cloud formation through orographic lifting, while also experiencing enhanced wind speeds that affect evaporation rates. The orientation of slopes relative to prevailing winds and sun angles influences local precipitation patterns. South-facing slopes in the northern hemisphere receive more direct sunlight, leading to increased evaporation and potentially different vegetation patterns that affect local humidity levels. North-facing slopes remain cooler and moister, sometimes supporting different ecosystems despite being only a few hundred meters away. Urban areas create their own distinctive precipitation patterns through multiple mechanisms. The urban heat island effect, caused by dark surfaces like asphalt and concrete, absorbing and retaining solar energy, can enhance convective activity and increase the frequency of afternoon thunderstorms. Cities also inject particles into the atmosphere that can serve as condensation nuclei, potentially affecting cloud formation and precipitation efficiency. The roughness of urban surfaces increases turbulence in the lower atmosphere, which can enhance vertical mixing and contribute to cloud development. Tall buildings can channel winds, creating corridors where air speeds increase and areas where air stagnates. These effects combine to create urban microclimates that can differ significantly from surrounding rural areas. Human activities beyond urbanization also influence local and regional precipitation patterns. Agriculture alters the land surface and changes evapotranspiration rates. Irrigation increases local humidity, while deforestation can reduce it. Large reservoirs create new sources of evaporation and can modify local temperature and humidity patterns. The measurement of precipitation reveals the complexity and variability of these natural processes. Rain gauges, the simplest instruments for measuring precipitation, can show dramatic differences in rainfall over distances of just a few kilometers. This spatial variability reflects the complex interplay of atmospheric processes operating at different scales. Modern weather radar systems can detect precipitation while it's still falling through the atmosphere, providing detailed three-dimensional views of storm structure and intensity. These systems reveal the intricate internal organization of precipitation systems, with updrafts and downdrafts, areas of heavy and light precipitation, and complex air motions that determine exactly where rain will reach the ground. Satellite observations provide a global perspective on precipitation patterns, revealing how storm systems develop and move across entire continents and ocean basins. These observations have revolutionized our understanding of how tropical systems form and intensify, how atmospheric rivers transport moisture across vast distances, and how climate patterns influence precipitation on seasonal and annual timescales. The combination of ground-based, airborne, and satellite observations allows meteorologists to create detailed analyses of current weather conditions and make increasingly accurate forecasts of future precipitation. Numerical weather prediction models divide the atmosphere into millions of grid cells and use the fundamental equations of physics to calculate how conditions in each cell will evolve over time. These models represent one of humanity's most successful applications of physics and mathematics to practical problems. They can predict the formation of storms days before they develop, track their movement across continents, and estimate rainfall amounts with remarkable accuracy. Yet they also reveal the inherent limits of predictability in chaotic systems like the atmosphere. Small uncertainties in initial conditions grow exponentially over time, eventually overwhelming even perfect models. This fundamental limitation means that detailed weather forecasts remain useful for only about a week, though seasonal and climate predictions can provide valuable information about longer-term trends and probabilities. The physics governing precipitation formation operates consistently regardless of scale. From individual cloud droplets to global circulation patterns. The same principles that determine whether a single droplet will evaporate or continue growing also influence whether entire storm systems will intensify or weaken. This consistency allows scientists to understand and predict atmospheric behavior across an enormous range of scales. Molecular-level processes in cloud droplets connect directly to continental-scale weather patterns through a continuous chain of physical cause and effect. Water molecules in cloud droplets vibrate with thermal energy that depends on temperature. When droplets collide, their kinetic energy determines whether they will merge or bounce apart. The electrical charges that develop on droplets and ice crystals influence their interactions and growth rates. These microscopic processes, multiplied across countless particles within a cloud, determine the macroscopic behavior we observe as precipitation. The formation of precipitation requires a delicate balance of competing processes. Droplets must grow large enough to overcome the updrafts that keep them suspended, but they must also avoid evaporating as they fall through potentially dry air below the cloud. Ice crystals must reach sufficient size to survive melting as they descend through warmer layers. Temperature profiles within clouds and below them play crucial roles in determining precipitation type and intensity. A shallow warm layer aloft can cause snow to melt and refreeze, creating sleet or freezing rain. A deep, warm layer leads to complete melting and liquid precipitation. These temperature structures depend on the overall atmospheric pattern and can vary significantly over short horizontal distances. The efficiency of precipitation formation varies among different types of clouds and weather systems. Warm clouds, where temperatures remain above freezing throughout, rely primarily on collision and coalescence processes. These clouds often produce light to moderate rainfall, but rarely generate the intense precipitation associated with severe thunderstorms. Cold clouds, extending well above the freezing level, can utilize both collision processes and ice crystal growth mechanisms. The Bergeron-Fine-Dyson process, where ice crystals grow at the expense of surrounding water droplets, can rapidly produce large precipitation particles. This process explains why many of the world's heaviest rainfall events involve clouds with significant ice content, even in tropical regions. The vertical development of clouds depends on atmospheric stability and the availability of moisture at different levels. A deep layer of moist air allows clouds to grow tall without encountering dry air that would inhibit further development. Conversely, dry layers aloft can cap cloud growth and prevent precipitation formation, even when surface conditions seem favorable. Wind shear, the change in wind speed and direction with altitude, affects cloud structure and precipitation efficiency. Light wind shear allows thunderstorms to develop vertically and produce heavy rainfall over relatively small areas. Strong wind shear can tilt clouds and spread precipitation over larger areas while reducing peak intensities. The organization of convective systems into lines, clusters, or supercells depends on wind shear patterns and atmospheric instability. Each organizational mode produces different precipitation patterns, from the brief intense downpours of isolated thunderstorms to the widespread long-lasting rainfall of organized squall lines. Frontal systems represent another major category of precipitation-producing weather patterns. These form along boundaries between air masses of different temperatures and humidities. Cold fronts, where dense cold air displaces warmer air, typically produce narrow bands of intense precipitation, followed by clearing skies. Warm fronts, where warm air gradually overrides cooler air, create broader areas of lighter, longer-lasting precipitation. Occluded fronts develop when cold fronts overtake warm fronts, creating complex three-dimensional structures with multiple precipitation areas. These systems often produce the most persistent and widespread precipitation events, sometimes lasting several days and affecting areas covering thousands of square kilometers. The movement and evolution of frontal systems depend on the large-scale atmospheric pattern, particularly the position and strength of jet streams. Rapidly moving fronts associated with strong jet streams tend to produce shorter duration but more intense precipitation. Slow-moving or quasi-stationary fronts can produce flooding rains as they focus moisture transport and precipitation formation over the same areas for extended periods. Low-pressure systems, or cyclones, represent organized circulation patterns that can produce precipitation through multiple mechanisms simultaneously. The convergent flow around low-pressure centers forces air to rise, promoting cloud formation. The associated fronts create additional lifting mechanisms. The overall circulation pattern can focus moisture transport from vast oceanic source regions. Tropical cyclones represent the most intense form of low-pressure systems, capable of producing extreme precipitation rates through their combination of very warm sea surface temperatures, minimal wind shear, and highly organized circulation patterns. These systems can transport enormous quantities of moisture from tropical oceans and deposit it as heavy rainfall when they encounter land areas or cooler waters. The precipitation patterns within tropical cyclones reflect their internal structure. The eye wall typically produces the heaviest rainfall, while spiral bands create intermittent areas of intense precipitation, separated by relatively lighter rain areas. As these systems move over land and weaken, they often produce flooding rains over areas far from the coast. Extratropical cyclones, the low-pressure systems that dominate weather patterns in mid-latitudes, produce precipitation through different mechanisms than their tropical counterparts. These systems derive their energy from temperature contrasts rather than warm ocean water, and their precipitation patterns reflect the associated frontal structures and air mass characteristics. The life cycle of extratropical cyclones follows predictable patterns of development, intensification, and decay. Young cyclones often produce light precipitation over broad areas. Mature systems with well-developed frontal structures create distinct precipitation patterns associated with each front. Aging cyclones may produce widespread light precipitation as their frontal structures weaken and become diffuse. The seasonal migration of storm tracks reflects the changing position of jet streams and the thermal contrast between land and ocean. During winter, when temperature contrasts reach their maximum, storm systems tend to be more intense and follow more southerly tracks. Summer storms are often weaker but can produce locally intense precipitation through convective processes. Regional climate patterns create distinctive seasonal precipitation regimes that vary around the world. Mediterranean climates feature wet winters and dry summers. Continental climates experience peak precipitation during summer months, when convective activity reaches its maximum. Coastal climates often show less seasonal variation due to the moderating influence of nearby oceans. These regional patterns reflect the interaction of global circulation features with local geographic factors. Mountain ranges, large lakes, ocean currents, and land-sea contrasts all contribute to the development of regional precipitation climatologies. The concept of water balance provides a framework for understanding how precipitation relates to other components of the hydrologic cycle. In any region, precipitation must balance evaporation, transpiration, runoff, and changes in soil moisture storage. This balance varies seasonally and annually, creating periods of water surplus and deficit. Drought conditions develop when precipitation falls consistently below normal levels, depleting soil moisture and reducing stream flow. The development and persistence of drought depend on atmospheric circulation patterns that favor high pressure and suppress storm development. These patterns can persist for months or years, creating severe water shortages. Conversely, flood conditions often result from precipitation patterns that concentrate large amounts of rain in short periods or over areas with limited capacity to absorb or channel the water. The same atmospheric patterns that produce beneficial rainfall can become destructive when they persist too long or affect areas unprepared for extreme precipitation. Climate change is modifying precipitation patterns through its effects on atmospheric moisture content, temperature gradients, and circulation patterns. Warmer air can hold more moisture, potentially intensifying precipitation events when conditions favor storm development. Changed temperature gradients may alter storm tracks and the seasonal timing of precipitation. These changes don't occur uniformly around the world. Some regions may experience increased precipitation while others become drier. The timing of precipitation may shift, with implications for agriculture, water supply, and ecosystem function. Understanding these evolving patterns requires careful analysis of long-term observations and sophisticated climate models. The measurement and monitoring of precipitation continue to evolve with advancing technology. Ground-based radar networks provide increasingly detailed observations of storm structure and rainfall rates. Satellite-based precipitation estimates extend coverage to remote areas where surface observations are sparse. Advanced computer models incorporate more detailed physics and higher resolution to improve forecasting accuracy. These technological advances enhance our ability to predict and prepare for precipitation extremes, from flash floods to extended droughts. Early warning systems can provide hours or days of advance notice for dangerous weather conditions. Seasonal forecasts help water managers and farmers prepare for expected wet or dry conditions. Despite these advances, significant uncertainties remain in our understanding of precipitation processes. Cloud microphysics involves complex interactions among water droplets, ice crystals, and aerosol particles that are difficult to observe and model accurately. The role of small-scale turbulence in cloud development and precipitation formation remains an active area of research. The interaction between natural climate variability and human-induced climate change creates additional complexity in understanding long-term precipitation trends. Separating the effects of greenhouse gas increases from natural oscillations requires careful statistical analysis and long-term data sets. Future research priorities include improving the representation of cloud processes in climate models, better understanding of extreme precipitation events, and enhanced prediction of seasonal and sub-seasonal precipitation patterns. These advances will help societies adapt to changing precipitation patterns and reduce the impacts of weather-related disasters. The study of precipitation connects fundamental physics with practical applications that affect billions of people. From the molecular processes that govern droplet growth to the global circulation patterns that transport moisture around the planet, precipitation research spans an enormous range of scales and disciplines. Understanding how rain forms and where it falls requires insights from thermodynamics, fluid mechanics, electrodynamics, and statistical physics. It involves observations from ground-based instruments, aircraft, and satellites. It requires mathematical models that solve complex equations on powerful computers. Yet despite this complexity, the fundamental processes remain elegantly simple. Water evaporates, air rises and cools, moisture condenses, and gravity pulls the resulting precipitation back to Earth. These basic steps, repeated countless times and in countless variations, create all the precipitation patterns we observe. The predictability within this apparent complexity allows farmers to plan their crops, engineers to design flood control systems, and meteorologists to forecast tomorrow's weather. It enables water managers to prepare for droughts and urban planners to design drainage systems. In the quiet moments between storms, when the atmosphere rests in temporary equilibrium, we can appreciate the intricate balance of forces that govern precipitation. Invisible water vapor drifts through the air around us, carrying the potential for future rain. Temperature and pressure gradients create gentle air motions that will eventually organize into weather systems. The Earth's rotation slowly deflects these motions, setting up the circulation patterns that will determine where tomorrow's storms will form. This hidden choreography continues day and night, season after season, year after year. Solar energy drives evaporation from distant oceans. Atmospheric rivers transport moisture across continents. Mountains lift air masses and squeeze out their moisture. All these processes operate according to physical laws discovered by scientists, yet they create patterns of beauty and complexity that inspire wonder and contemplation. The rain that falls outside your window connects you to this vast, interconnected system. Those drops began their journey in far-off seas, traveled invisible highways through the atmosphere, and now complete their cycle by returning to the earth. Some will soak into soil and nourish plants. Others will flow into streams and rivers, beginning new journeys toward the sea. This endless circulation of water between earth and sky represents one of the planet's most fundamental rhythms. It has continued for billions of years, shaping the surface of the earth, enabling the evolution of life, and creating the climate patterns that define different regions of our world. In understanding how rain decides where to fall, we glimpse the elegant simplicity underlying atmospheric complexity. Physical laws operating at the molecular level combine with global-scale processes to create the weather patterns we experience. Each raindrop represents the intersection of countless influences, from the temperature of distant oceans to the microscopic particles that serve as condensation nuclei. This scientific understanding doesn't diminish the wonder of precipitation. Instead, it reveals the remarkable sophistication of natural processes that operate continuously around us. The atmosphere functions as a vast, three-dimensional ocean of air, constantly in motion, constantly redistributing energy and moisture around the planet. As we rest in the gentle sound of falling rain, we can appreciate both its immediate presence and its connection to the larger systems that sustain our planet. The water cycle continues its ancient rhythm, driven by the same physical forces that have shaped the Earth's climate throughout its history. In this timeless process, we find both scientific understanding and peaceful contemplation of our place within the natural world. The next time rain begins to fall, listen to its quiet message about the invisible forces that shape our world. Feel the connection to distant oceans, high-altitude winds, and the countless processes that brought those water molecules to this moment and place. In the gentle percussion of raindrops, we hear the heartbeat of a living planet, the sound of water completing another cycle in its eternal journey between earth and sky. The rhythm of precipitation extends far beyond individual storm systems, weaving itself into the fabric of seasons and years through patterns so vast and enduring that entire civilizations have built their calendars around them. These larger cycles operate with a patience that spans decades and centuries, yet their influence touches every living thing on Earth with the same gentle persistence as a single raindrop soaking into soil. Seasonal precipitation patterns emerge from the Earth's slow dance around the sun, a choreography that has remained unchanged for millions of years. As our planet traces its elliptical path through space, the angle of sunlight striking different regions shifts gradually, creating the thermal rhythms that drive seasonal weather changes. This astronomical ballet determines when monsoons will arrive, when Mediterranean rains will begin, and when the dry seasons will grip various corners of the world. The migration of the sun's most direct rays between the tropics of Cancer and Capricorn creates a seasonal breathing pattern in the atmosphere. During Northern Hemisphere summer, intense solar heating over the Asian landmass creates vast low-pressure areas that draw moisture-laden air from the surrounding oceans. This thermal breathing draws the intertropical convergence zone northward, bringing life-giving rains to regions that depend entirely on this seasonal shift. The monsoon systems that affect nearly half of humanity operate through principles as reliable as the tides, yet infinitely more complex in their execution. The differential heating between massive continents and adjacent oceans creates pressure gradients that extend vertically through the entire depth of the troposphere. These gradients establish wind patterns that can transport moisture across thousands of kilometers, from tropical seas to inland agricultural regions where billions of people await the seasonal rains. In the Indian subcontinent, the timing of monsoon arrival varies by only a few weeks from year to year, despite the enormous complexity of the atmospheric processes involved. This remarkable consistency emerges from the fundamental physics of thermal contrast and pressure gradients. As the Tibetan Plateau heats during late spring and early summer, it creates a massive thermal low-pressure system that acts like a continental-scale vacuum cleaner, drawing moist air inland from the Indian Ocean. The journey of monsoon moisture begins over warm tropical waters, where evaporation rates reach their peak during the hottest months. Trade winds gather this moisture and transport it toward the heating continents in vast atmospheric rivers that can span entire ocean basins. When these moisture-laden air masses encounter the rising terrain of coastal mountains and interior plateaus, they release their cargo in torrential downpours that can deliver 80% of a region's annual precipitation in just a few months. The retreat of monsoon systems follows equally predictable patterns as continents cool during autumn and winter months. High-pressure systems develop over the cold land masses, reversing the pressure gradients and sending dry air masses back toward the oceans. This seasonal reversal creates the dry phases that are just as crucial as the wet phases for the ecosystems and agricultural systems that have evolved with these rhythms. Mediterranean climate regions experience their own distinctive seasonal precipitation patterns, driven by the seasonal migration of storm tracks and high-pressure systems. During winter months, these regions lie in the path of storms, guided by the polar jet stream. During summer, they fall under the influence of subtropical high-pressure systems that deflect storms to higher latitudes, creating the characteristic dry summers and wet winters. The reliability of these seasonal patterns allowed ancient civilizations to develop sophisticated agricultural systems and water management techniques. The timing of planting and harvesting, the construction of irrigation systems, and the storage of water during wet seasons all depend on the predictable arrival and departure of seasonal rains. Yet within these large-scale patterns, local variations create a tapestry of microclimates that can vary dramatically over short distances. Valley floors may experience different precipitation patterns than surrounding hillsides. Coastal areas may receive moisture from sea breezes while interior regions remain dry. Urban areas may generate their own precipitation patterns through heat island effects and altered surface roughness. The thermal properties of different surface materials create subtle but persistent influences on local precipitation patterns. Forests maintain higher humidity levels through transpiration, often generating afternoon thunderstorms through enhanced convection. Grasslands and agricultural areas create different thermal and moisture patterns that influence local cloud formation. Even the color and texture of soil can affect local evaporation rates and atmospheric heating. Water bodies create their own distinctive precipitation patterns through their thermal inertia and moisture contributions. Large lakes can generate lake-effect snow and rain when cold air masses pass over their relatively warm surfaces. Rivers and reservoirs add moisture to the local atmosphere and can trigger cloud formation along their corridors. Wetlands maintain high humidity levels that influence precipitation patterns across much larger areas. The interaction between vegetation and precipitation creates feedback loops that can persist for decades or centuries. Forests generate their own rainfall through transpiration and local atmospheric effects, while deforestation can reduce precipitation and create drier conditions. These vegetation-precipitation feedbacks help explain why some regions maintain stable wet or dry climates over long periods. Agricultural practices influence precipitation patterns through changes in surface properties and moisture availability. Irrigation increases local humidity and can enhance thunderstorm development. Crop selection affects transpiration rates and surface roughness. Even the timing of planting and harvesting can influence local atmospheric conditions during critical periods for storm development. The urban environment creates distinctive precipitation patterns through multiple mechanisms operating simultaneously. The urban heat island effect enhances convection and can increase thunderstorm frequency and intensity over cities. Tall buildings create turbulence and vertical motion that can trigger cloud formation. Industrial activities inject particles into the atmosphere that can serve as condensation nuclei or inhibit precipitation formation. Air pollution affects precipitation formation through its influence on cloud microphysics and atmospheric chemistry. Certain types of particles can enhance cloud formation by providing condensation nuclei, while others can inhibit precipitation by creating clouds with many small droplets that are less likely to collide and grow into raindrops. The relationship between air quality and precipitation represents an active area of atmospheric research with important implications for urban water resources. The measurement of precipitation reveals the enormous spatial and temporal variability inherent in atmospheric processes. Rain gauge networks show how precipitation can vary by factors of 2 or 3 over distances of just a few kilometers. This variability reflects the complex interplay of processes operating at different scales, from individual cloud droplets to continental weather patterns. Modern precipitation measurement techniques provide increasingly detailed views of how rain forms and falls. Weather radar systems can observe precipitation while it's still aloft, revealing the three-dimensional structure of storms and the processes occurring within them. Satellite observations provide global coverage of precipitation patterns, showing how moisture moves through the atmosphere on planetary scales. The combination of ground-based, airborne, and satellite observations allows scientists to construct detailed analyses of precipitation processes across all relevant scales. These observations reveal consistent physical principles operating from the formation of individual raindrops to the development of continental-scale weather systems. Numerical weather prediction models represent humanity's most sophisticated attempt to predict atmospheric behavior through the application of physical principles. These models divide the atmosphere into millions of grid cells and solve the fundamental equations of fluid motion, thermodynamics, and moisture conservation to predict future weather conditions. The success of these models demonstrates the deterministic nature of atmospheric processes, even within a chaotic system. The accuracy of precipitation forecasts has improved dramatically over recent decades, as models have incorporated more detailed physics and higher spatial resolution. Modern models can predict the formation and movement of individual thunderstorms hours before they develop, track the progress of large storm systems across continents, and provide useful guidance for seasonal precipitation patterns months in advance. Yet significant challenges remain in precipitation prediction, particularly for extreme events and at local scales. The chaotic nature of the atmosphere means that small uncertainties in initial conditions grow exponentially over time, limiting the useful range of detailed forecasts. Precipitation processes involve complex interactions among multiple physical mechanisms that occur at scales smaller than model resolution. Climate prediction operates on different principles than weather forecasting, focusing on long-term averages and patterns rather than specific events. Climate models can predict seasonal and annual precipitation patterns with considerable skill, providing valuable information for water resource management, agricultural planning, and disaster preparedness. The physics of precipitation formation provides a unifying framework for understanding atmospheric behavior across all scales. The same molecular processes that govern droplet growth in individual clouds also influence the development of planetary-scale circulation patterns. Energy conservation, mass conservation, and momentum conservation operate consistently from microscopic to global scales. This consistency allows scientists to understand atmospheric behavior as a continuous hierarchy of processes, each level influenced by smaller scale processes and influencing larger scale patterns. Cloud droplet interactions affect cloud properties, which influence storm development, which shapes regional weather patterns, which contribute to global climate systems. The predictability within atmospheric chaos emerges from the operation of physical laws that remain constant despite the enormous complexity of their interactions. Temperature gradients create pressure gradients that drive air motion. Rising air cools and can reach saturation, leading to cloud formation. Gravity pulls precipitation particles downward when they become large enough to overcome atmospheric support. These fundamental processes create order within apparent randomness. allowing scientists to understand and predict atmospheric behavior despite its chaotic nature. The atmosphere follows physical laws with the same reliability as any other natural system, even when the specific outcomes remain uncertain. The study of precipitation connects pure science with practical applications that affect every aspect of human society. Understanding cloud formation helps improve weather forecasts. Knowledge of precipitation processes guides the design of flood control systems. Insights into climate patterns inform agricultural planning and water resource management. This connection between fundamental research and practical applications demonstrates the value of scientific understanding in addressing real-world challenges. The same physical principles that explain how raindrops form also help engineers design more effective weather modification techniques and water harvesting systems. The global water cycle operates as a vast, interconnected system that links every part of our planet through the movement of water between different reservoirs. Precipitation represents just one component of this cycle, but it serves as the primary mechanism for redistributing fresh water from the oceans to the continents. This redistribution makes terrestrial life possible and shapes the character of different regions around the world. The residence time of water in different parts of the hydrologic cycle varies enormously, from days in the atmosphere to thousands of years in groundwater systems. This variation in residence times creates a complex temporal structure within the water cycle, where some components respond rapidly to changes while others maintain long-term stability. Atmospheric moisture has the shortest residence time of any component in the water cycle, with an average of only about 10 days between evaporation and precipitation. This rapid turnover means that the atmosphere's moisture content can change quickly in response to changing evaporation rates or circulation patterns. Yet the short residence time also provides stability, preventing the atmosphere from accumulating excessive moisture that could lead to permanent cloud cover. The ocean component of the water cycle operates on much longer timescales, with residence times measured in thousands of years. This thermal inertia provides stability to global climate patterns and helps buffer short-term variations in atmospheric conditions. Ocean currents transport heat and moisture around the globe, creating the thermal contrasts that drive atmospheric circulation and precipitation patterns. Groundwater systems operate on the longest timescales of any component in the water cycle, with some aquifers containing water that fell as precipitation tens of thousands of years ago. These systems provide long-term water storage that can sustain rivers and springs through extended dry periods. The slow movement of groundwater creates a natural buffer against short-term precipitation variations. The interaction among different components of the water cycle creates complex feedback mechanisms that help maintain global climate stability. Increased evaporation from warming oceans provides more atmospheric moisture for precipitation, but it also increases cloud cover that can reflect more sunlight back to space. Changes in precipitation patterns can affect vegetation, which influences evapotranspiration rates and atmospheric moisture content. These feedback mechanisms operate across multiple timescales, from the immediate response of cloud formation to evaporation, to the long-term effects of vegetation changes on regional climate patterns. Understanding these feedbacks requires careful analysis of observations and sophisticated modeling techniques that can capture processes operating across different scales. Climate variability adds another layer of complexity to precipitation patterns through oscillations and cycles that operate on timescales from years to decades. The El Niño Southern Oscillation represents the most well-known example of climate variability, affecting precipitation patterns across much of the globe through its influence on atmospheric and oceanic circulation. During El Niño events, warming of tropical Pacific waters alters atmospheric circulation patterns, shifting storm tracks and changing precipitation patterns across large portions of the Americas, Asia, and Australia. These changes can persist for months or even years. creating prolonged wet or dry conditions that affect agriculture, water supplies, and natural ecosystems. La Niña events produce complementary effects, cooling tropical Pacific waters and shifting precipitation patterns in the opposite direction. The irregular timing and intensity of these oscillations make long-term precipitation prediction challenging, even though the physical mechanisms are well understood. Other climate oscillations operate on different timescales and affect different regions. The North Atlantic Oscillation influences weather patterns across Europe and eastern North America through its effects on the position and strength of storm tracks. The Arctic Oscillation affects the behavior of the polar jet stream, influencing winter weather patterns across much of the Northern Hemisphere. These climate oscillations demonstrate the interconnected nature of the global climate system, where changes in one region can affect weather patterns thousands of kilometers away. The atmosphere and oceans function as a single, coupled system that redistributes energy and moisture around the planet through complex circulation patterns. The study of past climate variations provides insights into the natural range of precipitation variability and the mechanisms that control long-term climate changes. Paleoclimate records from tree rings, ice cores, and sediment cores reveal precipitation patterns extending back thousands of years, showing both the stability and variability of regional climate systems. These long-term records reveal that current precipitation patterns represent just one moment in the ongoing evolution of global climate. Past variations included periods of much greater aridity and much higher precipitation in various regions, driven by changes in solar radiation, atmospheric composition, and ocean circulation patterns. Understanding natural climate variability helps scientists distinguish between natural variations and human influences on precipitation patterns. This distinction becomes increasingly important as greenhouse gas concentrations continue to rise and their effects on global climate become more pronounced. Human activities are beginning to influence precipitation patterns through multiple mechanisms operating at local, regional, and global scales. Urbanization creates heat islands that affect local convection and precipitation patterns. Land use changes alter evapotranspiration rates and surface properties that influence regional climate. Greenhouse gas emissions are changing global temperature patterns and atmospheric moisture content. The warming climate is intensifying the global water cycle through increased evaporation rates and higher atmospheric moisture content. This intensification doesn't produce uniform changes in precipitation, but rather tends to make wet regions wetter and dry regions drier, while increasing the frequency and intensity of extreme precipitation events. Regional patterns of climate change vary considerably, with some areas experiencing increased precipitation, while others become drier. The Arctic is experiencing particularly rapid changes, with warming temperatures altering precipitation patterns and the balance between rain and snow. Tropical regions may experience changes in monsoon timing and intensity that affect billions of people. Mountain regions face unique challenges from climate change, as warming temperatures affect the balance between rain and snow and alter the timing of snowmelt. These changes affect water supplies for downstream communities and alter the seasonal patterns of river flow that many ecosystems and human activities depend upon. Coastal regions experience changing precipitation patterns due to rising sea surface temperatures and changing storm patterns. Some areas may experience more intense tropical cyclones, while others may see changes in the frequency and intensity of winter storms. Sea level rise adds another dimension to coastal precipitation impacts by affecting drainage patterns and flood risks. The response of vegetation to changing precipitation patterns creates additional complexity in understanding climate change impacts. Some ecosystems may expand their range in response to changing moisture availability, while others may contract or shift to different locations. These vegetation changes can influence local and regional precipitation patterns through altered evapotranspiration and surface properties. Agricultural systems face particular challenges from changing precipitation patterns, as crop selection and farming practices are closely adapted to historical climate patterns. Changes in the timing, intensity, or reliability of precipitation can require significant adaptations in agricultural practices and crop varieties. Water resource management becomes increasingly challenging as precipitation patterns change and become less predictable. Traditional approaches to reservoir operations, flood control, and water allocation may need revision as historical patterns no longer provide reliable guidance for future conditions. The measurement and monitoring of precipitation continues to evolve with advancing technology and changing needs. Traditional rain gauge networks provide long-term records essential for understanding climate change, but they may not adequately capture the spatial variability of precipitation, particularly in mountainous or remote regions. Radar and satellite observations provide increasing spatial and temporal detail about precipitation patterns, but these newer techniques must be carefully calibrated against ground-based measurements to ensure accuracy. The combination of multiple observation techniques provides the most comprehensive view of precipitation patterns and their changes over time. Advanced computer models continue to improve in their ability to simulate precipitation processes and predict future changes. Higher resolution models can capture more detailed local effects, while improved physics allows better representation of cloud processes and their interactions with atmospheric circulation patterns. Ensemble forecasting techniques provide probabilistic predictions that acknowledge the inherent uncertainty in weather and climate prediction. These approaches help decision-makers understand the range of possible outcomes and plan accordingly for different scenarios. The integration of observations, models, and theoretical understanding continues to advance our knowledge of precipitation processes and their role in the climate system. This integrated approach allows scientists to address increasingly complex questions about how precipitation patterns may change in the future and what these changes mean for human societies and natural ecosystems. Educational efforts help communicate the science of precipitation to broader audiences, building public understanding of weather and climate processes. This understanding becomes increasingly important as societies face the challenges of adapting to changing precipitation patterns and managing water resources more effectively. International cooperation in precipitation research and monitoring helps address the global nature of atmospheric processes and climate change. Weather systems cross national boundaries, and understanding their behavior requires observations and research efforts that span multiple countries and regions. The economic value of precipitation research and forecasting continues to grow as societies become more dependent on accurate weather and climate information. Improved precipitation forecasts help reduce flood damages, optimize agricultural production, and manage water resources more effectively. Research priorities continue to evolve as new questions emerge and new technologies become available. Understanding extreme precipitation events remains a high priority due to their disproportionate impacts on human societies. Improving seasonal and sub-seasonal precipitation prediction could provide enormous benefits for agriculture and water management. The study of precipitation interactions with air quality and atmospheric chemistry represents an emerging research area with important implications for human health and environmental quality. Understanding how pollution affects precipitation formation and how precipitation removes pollutants from the atmosphere requires interdisciplinary research approaches. As we continue to unravel the complexities of precipitation formation and distribution, we gain deeper appreciation for the elegant simplicity underlying atmospheric processes. The same physical principles that govern the behavior of individual molecules also control the formation of massive weather systems that span continents and affect billions of people. This unity of physical law across vastly different scales provides a foundation for understanding atmospheric behavior and predicting future changes. Whether examining the collision of cloud droplets or the circulation of planetary-scale weather systems, we find consistent application of conservation laws and thermodynamic principles. The atmosphere operates as a vast three-dimensional ocean of air, constantly in motion, constantly redistributing energy and moisture around the planet. Within this fluid envelope, precipitation represents the visible manifestation of invisible processes that operate continuously, quietly shaping the conditions that support all terrestrial life. In the gentle rhythm of falling rain, we hear the heartbeat of a living planet, the sound of water completing another cycle in its eternal journey between earth and sky. This ancient rhythm connects us to the fundamental processes that have shaped our world throughout its long history and continue to influence every aspect of life on Earth. The predictability within atmospheric complexity allows us to understand and anticipate these processes, to plan our activities around expected weather patterns, and to prepare for the variations that naturally occur within the climate system. This understanding represents one of humanity's greatest intellectual achievements, the successful application of physical principles to the challenge of understanding and predicting atmospheric behavior. Yet our growing knowledge also reveals the profound interconnectedness of atmospheric, oceanic, and terrestrial processes that create the climate system. Changes in one component affect all others through a web of feedback mechanisms that operate across multiple scales of space and time. As we look toward the future, our understanding of precipitation processes provides both challenges and opportunities. The challenges come from the need to adapt to changing precipitation patterns and manage water resources more effectively in a changing climate. The opportunities arise from our ability to apply scientific understanding to improve weather and climate prediction, develop more effective water management strategies, and design human systems that work harmoniously with natural processes. The quiet complexity of precipitation formation reminds us that the most fundamental processes often operate beyond our direct perception, yet their effects surround us every day. The invisible journey of water molecules from ocean to atmosphere to precipitation connects every drop of rain to the vast systems that govern our planet's climate. In appreciating this connection, we find both scientific wonder and practical wisdom. The science reveals the elegant operation of physical law in creating order from apparent chaos. The practical wisdom guides us toward more sustainable relationships with the natural systems that provide the water resources essential for all life. The atmosphere continues its ancient work, day and night, season after season, lifting moisture from the seas, transporting it across continents, and returning it to Earth as precipitation. This endless circulation creates the freshwater resources that sustain terrestrial ecosystems and human civilizations, while also serving as the primary mechanism for redistributing energy around the planet. Within this vast system, each raindrop represents the convergence of countless influences, from molecular-scale processes in cloud formation to planetary-scale circulation patterns. Understanding these influences allows us to appreciate both the complexity and the underlying simplicity of atmospheric processes. As we rest in the peaceful sound of gentle rain, we can contemplate our place within these larger systems that connect all parts of our planet through the movement of water and energy. The rain falling outside carries with it the history of its journey from distant seas, through invisible atmospheric highways, to this moment and place. This connection to planetary processes provides both humility and comfort. Humility in recognizing our dependence on systems vastly larger than ourselves. Comfort in understanding that these systems operate according to reliable physical principles that we can study, understand, and work with rather than against. The science of precipitation offers a window into the fundamental workings of our planet, revealing the processes that have operated for billions of years and continue to shape the conditions that make life possible. In understanding these processes, we gain both practical knowledge for managing our relationship with the natural world and deeper appreciation for the elegant complexity of the systems that surround us. The quiet percussion of raindrops against windows and rooftops marks another moment in the endless circulation of water between earth and sky. Each drop completes a journey that began with evaporation from distant oceans, continued through invisible atmospheric rivers, and now returns to earth to nourish the land and begin the cycle anew. In this gentle rhythm, we find connection to the timeless processes that have shaped our world and continue to sustain all life upon it. The rain speaks of invisible forces operating with quiet precision, of physical laws that govern the behavior of molecules and weather systems alike, of the profound interconnectedness that links every part of our planet through the simple yet miraculous circulation of water. As the soft sound of precipitation continues through the night, it carries with it the assurance that these ancient rhythms persist, that the fundamental processes that support life on Earth continue their patient work, and that we remain connected to these larger systems through every breath we take and every drop of water that falls from the sky above. The measurement of rainfall itself reveals another layer of the quiet precision that governs where precipitation falls. When we place a simple rain gauge in our garden, we're creating a small window into the vast atmospheric processes unfolding above us. That cylinder, collecting drops one by one, becomes part of a global network of observers documenting the Earth's water cycle with remarkable consistency. Modern weather stations scattered across continents record not just the amount of rain that falls, but when it begins, how intensely it arrives, and when it finally stops. These measurements, accumulated over decades, reveal patterns within patterns. Some locations receive their annual rainfall in just a few intense events, while others experience gentle, steady precipitation spread throughout the year. These differences aren't random variations, but reflect the predictable operation of atmospheric processes responding to local geography and seasonal rhythms. Weather radar extends our vision into the atmosphere itself, allowing us to observe precipitation while it's still forming and falling through the air above us. These systems send out radio waves that bounce off raindrops and ice crystals, creating detailed three-dimensional maps of storms in motion. Watching a radar image evolve over time reveals the internal structure of weather systems, their areas of heavy and light precipitation, their movement across the landscape, and their gradual strengthening or weakening. The images produced by weather radar resemble abstract art in motion, with colours representing different intensities of precipitation. Green areas indicate light rain, yellow shows moderate intensity, and red marks the heaviest downpours. These colour patterns shift and flow across the radar screen like slow-motion rivers of light, tracing the movement of moisture through the atmosphere with hypnotic precision. Satellite observations provide an even broader perspective, capturing the movement of weather systems across entire continents and ocean basins. From space, we can watch massive spiral storms develop over warm oceans, track the progress of frontal systems as they march across landscapes, and observe the seasonal migration of precipitation patterns as the Earth tilts through its annual journey around the Sun. These satellite images reveal the planet's atmosphere as a dynamic, ever-changing envelope of air and moisture. Cloud patterns swirl and flow in response to invisible forces, creating spirals, bands, and clusters that mark the locations where water vapor is condensing into visible droplets. The white swirls of clouds against the blue and brown surface of the Earth create a constantly shifting artwork painted by atmospheric physics. Computer models take these observations and use them to solve the fundamental equations that govern atmospheric behavior. These mathematical descriptions of fluid motion, heat transfer, and moisture transport allow meteorologists to predict how current weather patterns will evolve over the coming hours and days. The same physical principles that explain why a ball falls when dropped also govern the motion of air masses and the formation of precipitation. These numerical weather prediction models divide the atmosphere into millions of tiny boxes, each representing a small volume of air at a specific location and altitude. Within each box, the model calculates how temperature, pressure, humidity, and wind velocity will change over time due to the influence of neighboring boxes and the physical processes occurring within them. This computational approach transforms the qualitative understanding of atmospheric processes into quantitative predictions of future weather conditions. The accuracy of these predictions demonstrates the fundamentally deterministic nature of atmospheric processes. While individual raindrops follow chaotic paths as they fall through turbulent air, the larger patterns of precipitation formation and movement follow predictable physical laws. This predictability allows farmers to plan their activities, allows cities to prepare for flooding, and allows all of us to know whether to carry an umbrella when we leave home. Yet the atmosphere's sensitivity to small changes means that detailed predictions become less reliable as we look further into the future. A tiny difference in temperature or humidity can eventually grow into completely different weather patterns through the complex interactions within atmospheric systems. This limitation isn't a failure of our understanding, but rather reflects the chaotic nature of fluid systems operating under the influence of countless variables. The boundary between predictable and unpredictable atmospheric behavior shifts with the scale of the phenomena we're trying to forecast. Individual thunderstorms may develop in ways that are difficult to predict more than a few hours in advance, while seasonal patterns of precipitation can be anticipated months ahead of time. This difference reflects the different physical processes that control weather and climate, from the local effects that trigger individual storms to the global energy balance that determines seasonal patterns. Ocean temperatures play a crucial role in seasonal precipitation prediction because they change slowly and influence atmospheric patterns over vast regions. When tropical Pacific waters warm during El Niño events, they create atmospheric circulation changes that affect precipitation patterns across much of the globe. These effects can persist for months or even years, allowing meteorologists to predict seasonal rainfall patterns with considerable skill. The thermal mass of the oceans provides memory to the climate system, storing and slowly releasing the energy that drives atmospheric circulation. This oceanic memory allows seasonal forecasts to extend useful predictions far beyond the range of daily weather forecasts. While we cannot predict whether it will rain on a specific day next month, we can often predict whether the next season will be wetter or drier than normal. Regional climate patterns emerge from the interaction between global atmospheric circulation and local geographic features. The Mediterranean climate found along the western coasts of continents results from the seasonal migration of high-pressure systems and storm tracks. During winter, these regions lie in the path of storms driven by the jet stream. During summer, they fall under the influence of subtropical high pressure that deflects storms to higher latitudes. These regional patterns create distinctive seasonal rhythms that have remained consistent for thousands of years. The reliability of wet winters and dry summers in Mediterranean climates allowed ancient civilizations to develop agriculture and plan their activities around predictable precipitation patterns. Modern cities in these regions still depend on winter rains to fill reservoirs that must last through the dry summer months. Continental climate patterns reflect the thermal properties of large landmasses and their distance from oceanic moisture sources. Areas far from oceans experience greater temperature extremes and different precipitation patterns than coastal regions. The centers of large continents often receive most of their precipitation during summer months, when convective thunderstorms develop over the heated land surface. These continental effects create some of the world's most distinctive precipitation patterns. The Great Plains of North America receive peak precipitation during late spring and early summer, when moist air from the Gulf of Mexico interacts with the strong temperature gradients that develop over the heated continent. The timing of this precipitation maximum coincides perfectly with the growing season for crops, demonstrating how agricultural systems have evolved to take advantage of predictable climate patterns. Mountain effects on precipitation operate with mechanical precision, forcing air masses to rise and cool as they encounter topographic barriers. The resulting orographic precipitation creates some of the most dramatic rainfall gradients on Earth, with lush rainforests on windward slopes giving way to deserts just a few dozen kilometers away on the leeward side of mountain ranges. The Olympic Mountains of Washington State provide a textbook example of orographic precipitation effects. The western slopes, facing the prevailing westerly winds from the Pacific Ocean, receive over 4 meters of precipitation annually. The eastern slopes, in the rain shadow of the mountains, receive less than half a meter per year. This tenfold difference in precipitation occurs over a horizontal distance of less than 100 kilometers. These orographic effects operate through principles as reliable as gravity itself. When moist air encounters a mountain slope, physics leaves it no choice but to rise. As it ascends, decreasing atmospheric pressure causes it to expand and cool. This cooling reduces the air's capacity to hold moisture, forcing excess water vapor to condense into clouds and precipitation. The process occurs with mathematical precision, following the relationship between altitude, pressure, and temperature described by fundamental atmospheric equations. The rain shadow effect on the leeward side of mountains results from the same physical principles operating in reverse. Air that has deposited most of its moisture while rising over the mountains now descends the opposite slopes, warming and drying as it loses altitude. This descending air often becomes warmer and drier than it was before encountering the mountain, creating arid conditions even in regions that might otherwise receive adequate precipitation. Valley and slope effects create additional complexity in mountainous terrain, channeling airflows and creating local wind patterns that influence precipitation distribution. Cold air drainage at night can create temperature inversions that affect cloud formation. Valley breezes during the day can transport moisture upslope, enhancing afternoon thunderstorm development. These local effects combine with larger-scale orographic processes to create intricate patterns of wet and dry areas within mountain regions. Urban areas generate their own distinctive precipitation patterns through the modification of local atmospheric conditions. The urban heat island effect, created by dark surfaces absorbing and storing solar energy, enhances convective activity and can increase the frequency of afternoon and evening thunderstorms over cities. This enhancement often extends downwind of urban areas, creating precipitation patterns that follow the prevailing winds. The roughness of urban surfaces increases turbulence in the lower atmosphere, promoting vertical mixing that can contribute to cloud formation. Tall buildings create complex wind patterns that channel airflows and create areas of convergence where upward motion is enhanced. These mechanical effects combine with thermal effects to create urban microclimates that can differ significantly from surrounding rural areas. Air pollution affects urban precipitation through its influence on cloud formation processes. Some types of particles enhance cloud formation by providing additional surfaces where water vapor can condense. Others inhibit precipitation by creating clouds with many small droplets that are less likely to grow large enough to fall as rain. The relationship between air quality and precipitation remains an active area of research with important implications for urban water resources. Industrial activities and transportation systems inject various types of particles into the urban atmosphere, altering the natural distribution of cloud condensation nuclei. These changes can affect not only the amount of precipitation that falls over cities, but also its timing and intensity. Some studies suggest that urban areas may experience more frequent but less intense precipitation events due to these aerosol effects. The global distribution of precipitation reflects the combined influence of all these processes operating simultaneously across different scales. Tropical regions receive the most precipitation because they lie beneath the ascending branch of global atmospheric circulation, where warm, moist air rises and cools. Polar regions receive the least precipitation because cold air holds little moisture and atmospheric circulation patterns tend to be descending rather than ascending. Desert regions exist where atmospheric circulation patterns create persistent high pressure and descending air motion. The major desert belts around 30 degrees latitude coincide with the descending branches of atmospheric circulation cells that transport air poleward from the equator. This descending air warms and dries as it approaches the surface, creating stable atmospheric conditions that inhibit cloud formation and precipitation. Seasonal migration of precipitation patterns follows the sun's apparent movement between the tropics as the Earth orbits through its annual cycle. The intertropical convergence zone, marking the region of maximum atmospheric heating and ascending motion, moves northward during the northern hemisphere summer and southward during winter. This migration brings wet seasons to different regions at different times of the year, creating the monsoon patterns that affect billions of people. Ocean currents contribute to global precipitation patterns by transporting warm and cold water masses around the planet, affecting regional evaporation rates and atmospheric heating patterns. The Gulf Stream carries warm water northward along the eastern coast of North America, enhancing evaporation and contributing to precipitation across the North Atlantic region. Cold currents have the opposite effect, reducing evaporation and creating drier atmospheric conditions. The interaction between atmospheric and oceanic circulation creates feedback mechanisms that help stabilize global climate patterns while also allowing for natural variability. Changes in ocean temperatures can alter atmospheric circulation patterns, which in turn affect wind patterns and ocean currents. These coupled atmosphere-ocean interactions operate on timescales ranging from months to centuries, creating the natural climate variations that we observe in precipitation records. Paleoclimate records reveal that current precipitation patterns represent just one moment in the long-term evolution of global climate. Ice cores, tree rings, and other climate proxies show that past climates included periods of very different precipitation distributions, with some regions experiencing much wetter or drier conditions than they do today. These records help scientists understand the range of natural climate variability and the processes that drive long-term climate changes. The study of past climates also provides insights into how precipitation patterns respond to changes in atmospheric composition, solar radiation, and other external factors. These insights prove valuable for understanding how current changes in greenhouse gas concentrations might affect future precipitation patterns. The same physical processes that controlled past climate changes continue to operate today, providing a foundation for predicting future changes. Climate models use our understanding of atmospheric and oceanic processes to project how precipitation patterns might change as greenhouse gas concentrations continue to rise. These models consistently predict that warming temperatures will intensify the global water cycle, increasing evaporation rates and atmospheric moisture content. However, the resulting changes in precipitation won't be distributed uniformly around the globe. The warming climate tends to make wet regions wetter and dry regions drier, while increasing the frequency and intensity of extreme precipitation events. These changes reflect the basic physics of a warmer atmosphere's ability to hold more moisture and the tendency for atmospheric circulation patterns to intensify as temperature gradients change. Tropical regions may experience more intense monsoons, while subtropical deserts may expand poleward. Regional patterns of climate change vary considerably due to the influence of local geographic features and circulation patterns. Some regions may experience increased precipitation, while nearby areas become drier. Mountain regions face particular challenges, as warming temperatures affect the balance between rain and snow, altering seasonal patterns of water availability that many ecosystems and human communities depend upon. The Arctic experiences some of the most dramatic changes in precipitation patterns as warming temperatures alter the fundamental character of the region's climate. Increased evaporation from ice-free ocean areas provides more moisture for precipitation, while changing atmospheric circulation patterns affect storm tracks and seasonal weather patterns. These changes have implications far beyond the Arctic, influencing weather patterns across the entire Northern Hemisphere. Coastal regions face changing precipitation patterns due to rising sea surface temperatures and evolving storm patterns. Some areas may experience more intense tropical cyclones capable of producing extreme rainfall amounts. Others may see changes in winter storm patterns that alter seasonal precipitation distributions. Rising sea levels add another dimension to coastal precipitation impacts by affecting drainage systems and increasing flood risks. Adaptation strategies for changing precipitation patterns require understanding both the physical processes that control rainfall and the ways that human systems interact with natural water cycles. Traditional approaches to water management, flood control, and agricultural planning may need modification as historical precipitation patterns become less reliable guides for future conditions. Water resource management faces increasing challenges as precipitation becomes more variable and extreme events become more frequent. Reservoir operations may need to account for longer dry periods punctuated by more intense storms. Flood control systems may require upgrades to handle larger peak flows. Agricultural practices may need adjustment to cope with changing seasonal patterns of water availability. The measurement and monitoring of precipitation continue to evolve with advancing technology and growing recognition of the importance of accurate rainfall observations for both weather forecasting and climate research. Modern observing systems combine traditional rain gauges with sophisticated radar and satellite instruments to provide comprehensive coverage of precipitation patterns across all scales. Ground-based radar networks can observe precipitation in 3 dimensions, revealing the internal structure of storms and tracking their evolution over time. These observations provide crucial information for short-term weather forecasting and also contribute to our understanding of storm physics and precipitation processes. The detailed structure revealed by radar observations often shows surprising complexity even in apparently simple rain showers. Satellite-based precipitation estimates extend coverage to remote areas where surface observations are sparse, including vast ocean areas where most of the global water cycle operates. These satellite observations reveal global patterns of precipitation and their changes over time, providing essential information for climate research and seasonal forecasting. The combination of multiple satellite instruments allows scientists to estimate rainfall rates and track the movement of moisture through the atmosphere on planetary scales. Advanced computer models continue to improve in their ability to represent precipitation processes and predict future changes. Higher spatial resolution allows models to capture more detailed local effects, while improved representation of cloud physics leads to more realistic simulation of precipitation formation and intensity. These improvements enhance both weather forecasting and climate prediction capabilities. Ensemble forecasting techniques acknowledge the inherent uncertainty in predicting chaotic atmospheric systems by running multiple model simulations with slightly different initial conditions. The spread among ensemble members provides information about forecast uncertainty and helps identify situations where confidence is high or low. This probabilistic approach proves particularly valuable for predicting extreme events and seasonal climate patterns. The economic value of accurate precipitation forecasting continues to grow as societies become more dependent on weather-sensitive activities and more vulnerable to weather extremes. Improved rainfall predictions help reduce flood damages, optimize agricultural production, enhance water resource management, and support numerous other weather-sensitive decisions. The return on investment in meteorological research and observing systems far exceeds their costs through reduced weather-related losses and improved efficiency in weather-sensitive sectors. International cooperation in meteorological research and operations reflects the global nature of atmospheric processes and the benefits that all nations derive from improved understanding of precipitation and weather systems. Weather systems cross national boundaries freely, making international data sharing and coordinated research essential for effective forecasting and climate monitoring. Educational efforts help build public understanding of precipitation processes and climate science, enabling more informed decision-making about adaptation strategies and risk management. Understanding the physical basis for weather and climate helps people distinguish between natural variability and long-term changes, leading to more effective responses to both weather extremes and climate change. Research priorities continue to evolve as new questions emerge and new technologies become available. Understanding extreme precipitation events remains crucial due to their disproportionate impacts on human societies and natural ecosystems. Improving seasonal and subseasonal precipitation prediction could provide enormous benefits for agriculture, water management, and disaster preparedness. The interaction between precipitation and air quality represents an emerging research area with important implications for both atmospheric science and public health. Understanding how aerosol particles affect cloud formation and precipitation efficiency helps explain regional differences in rainfall patterns and guides efforts to improve air quality. The removal of pollutants by precipitation also affects atmospheric chemistry and the transport of contaminants through the environment. Advances in atmospheric chemistry research reveal complex interactions between precipitation formation and the composition of the atmosphere. Different types of particles affect cloud properties in different ways, influencing not only the amount of precipitation that forms, but also its acidity and chemical composition. These interactions have implications for ecosystem health, agricultural productivity, and water quality. The study of precipitation connects fundamental physics with practical applications that affect every aspect of life on Earth. Understanding cloud formation helps improve weather forecasts that protect lives and property. Knowledge of precipitation processes guides the design of infrastructure systems that must function reliably in variable weather conditions. Insights into climate patterns inform long-term planning for agriculture, water resources, and urban development. This connection between basic research and practical applications demonstrates the value of scientific understanding in addressing real-world challenges. The same physical principles that explain molecular behavior in cloud droplets also help engineers design more effective water harvesting systems and urban drainage networks. The predictability within atmospheric complexity provides both scientific satisfaction and practical benefits. Understanding that precipitation follows physical laws allows us to make useful predictions about future weather conditions and climate changes. This predictability enables societies to prepare for weather extremes, plan agricultural activities, and manage water resources more effectively. The global water cycle operates as Earth's circulatory system, continuously redistributing fresh water from the oceans to the continents and back again. Precipitation represents the primary mechanism for this redistribution, making terrestrial life possible and shaping the character of different regions around the world. The annual movement of approximately 100,000 cubic kilometers of water from sea to land through atmospheric transport creates the freshwater resources that sustain all continental ecosystems. This vast circulation operates with quiet efficiency, lifting moisture from warm ocean surfaces, transporting it across continents in invisible atmospheric rivers, and returning it to Earth as precipitation when atmospheric conditions favor condensation. The entire process requires no external energy beyond solar radiation, demonstrating the elegant simplicity of the physical principles that govern our planet's climate system. The residence time of water in different parts of the global water cycle creates a complex temporal structure that provides both rapid response to changing conditions and long-term stability. Atmospheric moisture responds quickly to changes in evaporation and circulation patterns, while groundwater systems provide storage that can sustain rivers and springs through extended dry periods. This range of response times helps buffer short-term variations while maintaining long-term water availability. Seasonal patterns in precipitation reflect the Earth's orbital dance around the Sun, creating rhythms that have remained consistent for thousands of years. These patterns provided the foundation for the development of agriculture and the establishment of human civilizations in regions where seasonal rains arrived with predictable regularity. The reliability of these astronomical controls on climate gives us confidence that seasonal patterns will continue, even as year-to-year variations and long-term changes add complexity to precipitation patterns. The influence of geography on precipitation patterns creates the distinctive regional climates that characterize different parts of our planet. From the monsoon rains of Asia to the Mediterranean climates of western coasts, from the orographic precipitation of mountain regions to the rain shadows of desert areas, the interaction between atmospheric processes and surface features creates a diverse tapestry of precipitation regimes that support an enormous variety of ecosystems and human activities. Local variations in precipitation patterns reflect the sensitivity of atmospheric processes to subtle differences in topography, land cover, and surface properties. These variations create microclimates that can support different plant and animal communities within relatively small areas. Understanding these local effects helps explain the rich biodiversity found in regions with complex topography and variable precipitation patterns. Human activities increasingly influence precipitation patterns through changes in land use, urban development, and atmospheric composition. These influences operate across multiple scales, from local effects of urbanization on convective activity to global effects of greenhouse gas emissions on atmospheric moisture content and circulation patterns. Understanding these human influences becomes increasingly important as populations grow and climate change accelerates. The measurement and prediction of precipitation represent one of humanity's most successful applications of physical science to practical problems. The ability to forecast weather conditions days in advance and predict seasonal climate patterns months ahead demonstrates our growing understanding of atmospheric processes and their underlying physical controls. Continued improvements in observing systems and computer models promise even better predictions in the future. The study of precipitation provides insights into the fundamental workings of our planet's climate system and its sensitivity to various influences. Understanding how precipitation patterns have varied in the past helps us anticipate how they might change in the future as atmospheric composition continues to evolve. This knowledge proves essential for planning adaptation strategies and managing the risks associated with changing weather patterns. Climate change adds urgency to precipitation research as societies seek to understand and prepare for evolving weather patterns. The intensification of the water cycle under warming conditions promises to create more extreme precipitation events, while also altering seasonal patterns and regional distributions of rainfall. Understanding these changes requires continued research into the physical processes that control precipitation formation and distribution. The interconnected nature of the global climate system means that changes in precipitation patterns in one region can affect weather and climate conditions elsewhere through atmospheric and oceanic teleconnections. These far-reaching effects demonstrate the importance of global cooperation in monitoring and understanding precipitation changes, and their broader implications for human societies and natural ecosystems. As we deepen our understanding of precipitation processes, we gain greater appreciation for the elegant complexity of the atmospheric system that sustains life on our planet. The same physical laws that govern the behavior of individual molecules also control the formation of massive weather systems that redistribute energy and moisture around the globe. This unity of physical principles across vastly different scales provides a foundation for understanding atmospheric behavior and predicting its future evolution. The quiet precision with which precipitation processes operate reflects the deterministic nature of physical laws, even within systems that exhibit chaotic behavior. While we cannot predict the exact path of individual raindrops, we can understand and predict the larger patterns of precipitation formation and distribution that emerge from the collective behavior of countless water molecules responding to atmospheric forces. In the gentle rhythm of falling rain, we witness the culmination of processes that connect every part of our planet through the circulation of water between Earth and atmosphere. This ancient rhythm continues day and night, season after season, maintaining the delicate balance of moisture that makes terrestrial life possible. The predictability of this rhythm, governed by unchanging physical laws, provides both scientific understanding and quiet reassurance that these fundamental processes will continue. The sound of rain against windows carries with it the story of invisible journeys completed, of water molecules that began their travels in distant oceans, soared through atmospheric highways invisible to our eyes, and now return to Earth to nourish the land and continue the eternal cycle. In this gentle percussion, we hear the heartbeat of a living planet, the quiet testimony of physical processes operating with mathematical precision to maintain the conditions that sustain all life. As precipitation continues its patient work through the night, redistributing moisture across the landscape and replenishing the reservoirs that sustain us, we can rest in the knowledge that these ancient rhythms persist unchanged. The same forces that have shaped our planet's climate for billions of years continue their quiet influence, governed by physical laws as reliable as sunrise, as constant as the tides, as enduring as the mountains themselves. In the soft whisper of rain on leaves, in the gentle patter of drops on rooftops, in the quiet murmur of water finding its way back to the sea, we find connection to the timeless processes that bind all life together through the simple yet miraculous circulation of water. This circulation requires no consciousness, no intention, no decision-making, yet it operates with a precision and reliability that enables the flourishing of countless species across every continent. The atmosphere continues its ancient work, lifting moisture from warm seas, carrying it across vast distances, and returning it to Earth when conditions favor condensation. This endless dance of evaporation and precipitation creates the freshwater resources that nourish forests, fill rivers, sustain agriculture, and provide the foundation for all terrestrial ecosystems. In its quiet persistence, we find both scientific wonder and peaceful assurance that these fundamental processes will endure, maintaining the delicate balance that makes our living planet possible. The invisible architecture of precipitation extends far beyond individual storm systems, weaving itself into patterns that span decades and centuries through the patient influence of ocean currents and their thermal memory. Deep beneath the surface of our seas, massive rivers of water flow in slow motion, carrying warmth and coolness across entire ocean basins in journeys that can take 1,000 years to complete. These thermohaline currents, driven by differences in water temperature and salinity, create a global conveyor belt that redistributes heat around the planet with the steady persistence of a heartbeat. Warm water flows poleward near the surface, while cold, dense water returns toward the equator in the deep ocean depths. This circulation influences regional temperatures across vast areas, which in turn affects evaporation rates and atmospheric moisture content. The Gulf Stream exemplifies this oceanic influence on precipitation patterns. This massive current carries warm Caribbean water northward along the eastern coast of North America, releasing heat and moisture into the atmosphere throughout its journey. The enhanced evaporation over these warm waters provides additional moisture for storm systems, influencing precipitation patterns from Florida to the North Atlantic region. When the Gulf Stream reaches the cold waters of the North Atlantic, it releases its remaining heat to the atmosphere and begins to sink, starting its slow journey back toward the tropics in the deep ocean. This heat release moderates temperatures across northwestern Europe, creating a climate much milder than other regions at similar latitudes. Without this oceanic heat transport, precipitation patterns across the entire North Atlantic region would be dramatically different. Similar oceanic influences operate in every ocean basin, creating regional climate patterns that persist for decades or centuries. The Kuroshio Current warms the coasts of Japan, enhancing evaporation and contributing to the intense precipitation that characterizes the East Asian monsoon. The California Current brings cold water southward along the western coast of North America, reducing evaporation and contributing to the arid conditions that prevail along much of this coastline. Changes in ocean circulation patterns can alter precipitation regimes across vast regions through their effects on atmospheric heating and moisture transport. The medieval warm period and the Little Ice Age both involve shifts in ocean circulation that affected rainfall patterns across Europe, Asia, and the Americas. These changes persisted for centuries, demonstrating the long-term influence of oceanic processes on global precipitation patterns. El Niño and La Niña events represent shorter-term variations in ocean atmosphere coupling that nonetheless produce profound changes in precipitation patterns across much of the globe. During El Niño events, warming of tropical Pacific waters alters atmospheric circulation patterns, shifting storm tracks and precipitation patterns from California to Australia to the Amazon basin. The physical mechanism behind these teleconnections involves the atmosphere's response to changes in oceanic heating patterns. Warm ocean water enhances evaporation and creates rising motion in the atmosphere above it. This rising motion affects atmospheric pressure patterns, which in turn influence wind patterns and storm tracks thousands of kilometers away. The atmosphere responds to oceanic changes like a vast musical instrument, with changes in one region creating harmonics that resonate around the globe. La Niña events produce complementary effects by cooling tropical Pacific waters and strengthening the normal patterns of atmospheric circulation. These cooling events often intensify existing precipitation patterns, bringing enhanced rainfall to already wet regions while making dry areas even more arid. The irregular timing and intensity of these oceanic oscillations add a layer of natural variability to precipitation patterns that makes long-term prediction challenging. The North Atlantic Oscillation represents another oceanic influence on precipitation, though its effects operate through different physical mechanisms than tropical Pacific variations. This oscillation involves changes in the temperature and pressure patterns across the North Atlantic basin, which affect the strength and position of the jet stream over Europe and eastern North America. When the North Atlantic Oscillation is in its positive phase, strong pressure gradients maintain a robust and relatively straight jet stream that guides storms toward northern Europe while deflecting them away from the Mediterranean region. During negative phases, weaker pressure gradients allow the jet stream to become more meandering, permitting storms to reach southern Europe while blocking them from northern regions. These Atlantic influences demonstrate how oceanic processes can reverse typical precipitation patterns, bringing drought to normally wet regions and unexpected rainfall to typically dry areas. The effects can persist for months or even years, creating sustained departures from normal precipitation patterns that affect agriculture, water resources, and natural ecosystems across large portions of two continents. Arctic sea ice adds another oceanic influence on precipitation patterns through its effects on regional heating and atmospheric circulation. The bright white surface of sea ice reflects most incoming solar radiation back to space, while dark ocean water absorbs this energy and warms the atmosphere above it. Changes in sea ice extent therefore alter regional heating patterns and can affect atmospheric circulation across the entire northern hemisphere. The dramatic reduction in Arctic sea ice extent over recent decades has enhanced evaporation from newly ice-free ocean areas, providing additional moisture for precipitation, while also altering temperature gradients that drive atmospheric circulation. These changes may be affecting the behavior of the polar jet stream and influencing weather patterns across North America, Europe, and Asia, though the exact mechanisms and their long-term implications remain subjects of active research. Volcanic eruptions represent another external influence on global precipitation patterns through their injection of particles and gases into the stratosphere. Major eruptions can reduce incoming solar radiation for months or years, cooling global temperatures and altering atmospheric circulation patterns. These cooling effects can shift precipitation patterns, often reducing rainfall in tropical regions while enhancing it at higher latitudes. The 1991 eruption of Mount Pinatubo in the Philippines provided a natural experiment in climate modification, cooling global temperatures by about 0.5 degrees Celsius for several years. The reduced solar heating weakened monsoon circulations and altered storm tracks around the world, demonstrating how external influences can temporarily override the normal patterns of atmospheric circulation and precipitation. Solar variations also influence precipitation patterns through their effects on global energy balance and atmospheric heating patterns. The 11-year solar cycle produces small but measurable changes in the amount of energy reaching Earth, which can affect regional precipitation patterns, particularly in tropical regions where solar heating drives monsoon circulations. Longer-term solar variations may have contributed to past climate changes, including the Little Ice Age, when reduced solar output may have weakened atmospheric circulation patterns and altered precipitation regimes across much of the Northern Hemisphere. These solar influences remind us that precipitation patterns reflect not only terrestrial processes, but also the cosmic environment in which our planet moves. The study of paleoclimate provides insights into how precipitation patterns have varied over much longer timescales, revealing the range of natural variability and the processes that drive long-term climate changes. Ice cores from Greenland and Antarctica contain detailed records of past precipitation, temperature, and atmospheric composition extending back hundreds of thousands of years. These paleoclimate records show that current precipitation patterns represent just one moment in the ongoing evolution of Earth's climate system. Past climates included periods when precipitation patterns were dramatically different from today, with some regions experiencing much wetter or drier conditions than they currently do. The Sahara Desert, for example, was much wetter during certain periods in the past, supporting grasslands and lakes where only sand dunes exist today. Tree ring records provide high-resolution information about precipitation variability over the past millennium, revealing the frequency and intensity of past droughts and wet periods. These records show that precipitation varies naturally on timescales from years to centuries, helping scientists distinguish between natural variability and human influences on climate patterns. Sediment cores from lakes and ocean basins extend our knowledge of precipitation changes even further into the past, showing how regional precipitation patterns have responded to past changes in ice sheets, ocean circulation, and atmospheric composition. These long-term records provide essential context for understanding current climate changes and projecting future precipitation patterns. The emergence of human influences on precipitation patterns represents a new chapter in the long history of Earth's climate system. Land use changes began affecting regional precipitation patterns thousands of years ago as agriculture expanded and forests were cleared. Urbanization creates local heat islands that enhance convective activity and can increase precipitation frequency and intensity over cities. Industrial activities inject various types of particles into the atmosphere that can affect cloud formation and precipitation processes. Some particles enhance precipitation by providing additional condensation nuclei, while others may inhibit precipitation by creating clouds with many small droplets that are less likely to grow large enough to fall as rain. Greenhouse gas emissions are beginning to alter global precipitation patterns through their effects on atmospheric temperature and moisture content. The warming atmosphere can hold more water vapor, intensifying the global water cycle and potentially increasing the frequency and intensity of extreme precipitation events. These changes don't occur uniformly around the world, but tend to make wet regions wetter and dry regions drier. Regional patterns of precipitation change vary considerably due to the complex interactions between global warming and local geographic and circulation factors. Some regions may experience increased precipitation, while nearby areas become drier. The timing of precipitation may shift, with implications for seasonal water availability and the ecosystems and agricultural systems that depend on predictable seasonal patterns. Mountain regions face particular challenges from changing precipitation patterns as warming temperatures affect the balance between rain and snow. Earlier snowmelt and reduced snowpack alter the seasonal timing of water availability, affecting both natural ecosystems and human water supplies. Many regions depend on mountain snowpack to provide water during dry summer months, making these changes especially significant. Coastal regions experience changing precipitation patterns due to rising sea surface temperatures and evolving storm patterns. Warmer oceans enhance evaporation and can intensify tropical cyclones, potentially increasing extreme precipitation events in some areas, while altering seasonal patterns in others. Rising sea levels add another dimension to coastal precipitation impacts by affecting drainage systems and increasing flood risks. The measurement and monitoring of precipitation continue to evolve as scientists seek to understand both current patterns and their changes over time. Traditional rain gauge networks provide essential long-term records, but may miss the spatial variability of precipitation, particularly in mountainous or remote regions where gauge density is low. Weather radar systems provide detailed three-dimensional observations of precipitation in real time, revealing the internal structure of storms and allowing meteorologists to track their evolution and movement. These systems can estimate rainfall rates across large areas and provide warnings of flash flooding when intense precipitation develops over urban areas or steep terrain. Satellite observations extend precipitation monitoring to global scales, including vast ocean areas where surface observations are sparse. Multiple satellite instruments working together can estimate rainfall rates and track the movement of moisture through the atmosphere, providing essential information for both weather forecasting and climate research. Advanced computer models integrate these observations with our understanding of atmospheric physics to create increasingly detailed simulations of precipitation processes. Higher resolution models can capture local effects of topography and land use, while improved representation of cloud physics leads to more realistic simulation of precipitation formation and intensity. Ensemble forecasting techniques acknowledge the inherent uncertainty in atmospheric prediction, by running multiple simulations with slightly different initial conditions. The spread among ensemble members provides information about forecast confidence and helps identify situations where extreme precipitation events are possible, even if their exact location and timing remain uncertain. Seasonal precipitation forecasting represents a growing area of capability as scientists develop better understanding of the oceanic and atmospheric processes that influence precipitation patterns months in advance. These forecasts prove valuable for agricultural planning, water resource management, and disaster preparedness, even though they cannot predict specific weather events. The economic value of precipitation research and forecasting continues to grow as societies become more weather sensitive and climate change increases the frequency of extreme events. Improved precipitation predictions help reduce flood damages, optimize agricultural production, enhance water resource management, and support numerous weather-sensitive decisions throughout the economy. International cooperation in precipitation research reflects the global nature of atmospheric processes and the shared benefits of improved understanding. Weather systems cross national boundaries freely, making international data sharing and coordinated research essential for effective monitoring and prediction of precipitation patterns. Educational efforts help build public understanding of precipitation processes and their role in the climate system. Understanding the physical basis for precipitation patterns helps people make informed decisions about water use, flood risk, and climate adaptation strategies. Science education also helps distinguish between natural climate variability and long-term trends, leading to more effective responses to both weather extremes and climate change. Research priorities continue to evolve as new technologies become available and new questions emerge about precipitation processes and their changes. Understanding extreme precipitation events remains crucial due to their disproportionate impacts on human societies and natural ecosystems. These events often result from the interaction of multiple factors operating simultaneously, making them challenging to predict and understand. Improving subseasonal precipitation prediction represents another priority, as forecasts spanning 2 weeks to 2 months could provide enormous benefits for agriculture, water management, and disaster preparedness. This timescale bridges the gap between weather forecasts and seasonal climate predictions, requiring understanding of atmospheric processes that operate on intermediate timescales. The interaction between precipitation and air quality represents an emerging research area with implications for both atmospheric science and public health. Understanding how aerosol particles affect cloud formation helps explain regional differences in precipitation patterns and guides efforts to improve air quality. The removal of pollutants by precipitation also affects atmospheric chemistry and the transport of contaminants through the environment. Advances in cloud physics research continue to reveal new details about precipitation formation processes. The role of ice crystals in precipitation formation, the effects of turbulence on droplet collisions, and the influence of electrical charges on cloud development all represent active areas of investigation that could improve our ability to predict precipitation intensity and distribution. Urban precipitation research focuses on understanding how cities affect local precipitation patterns and how urban design might be modified to work more harmoniously with natural hydrological processes. Green infrastructure, permeable surfaces, and urban forest management all represent strategies for managing urban precipitation impacts while potentially influencing local precipitation patterns. Agricultural meteorology examines the specific precipitation requirements of different crops and how changing precipitation patterns might affect agricultural productivity. Understanding the timing and intensity of precipitation needs helps develop drought-resistant crops and more efficient irrigation systems. This research becomes increasingly important as climate change alters traditional precipitation patterns in agricultural regions. Water resource management increasingly relies on sophisticated precipitation forecasting and climate projections to guide decisions about reservoir operations, flood control, and water allocation. Traditional approaches based on historical precipitation patterns may need revision as climate change makes the past a less reliable guide to future conditions. Ecosystem research examines how changing precipitation patterns affect natural communities and biodiversity. Many ecosystems are closely adapted to specific precipitation regimes, and changes in rainfall amount, timing, or intensity can affect species composition and ecosystem function. Understanding these relationships helps guide conservation efforts and ecosystem management strategies. The study of precipitation connects fundamental atmospheric physics with practical applications that affect every aspect of life on Earth. Understanding droplet formation helps improve weather forecasts that protect lives and property. Knowledge of precipitation processes guides the design of infrastructure systems that must function reliably under variable weather conditions. This connection between basic research and practical applications demonstrates the value of continued investment in atmospheric science research. The same physical principles that explain molecular behavior in clouds also help engineers design more effective water collection systems and urban drainage networks. The predictability within atmospheric complexity provides both intellectual satisfaction and practical benefits. Understanding that precipitation follows physical laws allows us to make useful predictions about future weather conditions and climate changes. This predictability enables societies to prepare for weather extremes, plan agricultural activities, and manage water resources more effectively. The global water cycle represents one of Earth's most fundamental processes, continuously redistributing fresh water from the oceans to the continents through atmospheric transport. This circulation makes terrestrial life possible and shapes the character of different regions around the world. The reliability of this circulation, governed by unchanging physical laws, provides the foundation for all terrestrial ecosystems. Seasonal patterns in precipitation reflect the astronomical controls on Earth's climate, creating rhythms that have persisted for millions of years. These patterns provided the foundation for the evolution of life on land and the development of human civilizations in regions where seasonal rains arrived with predictable regularity. Regional variations in precipitation patterns reflect the complex interactions between global atmospheric circulation and local geographic features. These variations create the diverse array of climates that characterize different parts of our planet, from tropical rainforests to temperate grasslands to arid deserts. Human activities increasingly influence precipitation patterns through multiple mechanisms operating at different scales. Understanding these influences becomes essential for managing water resources, planning urban development, and adapting to climate change. The same scientific understanding that explains natural precipitation processes also guides efforts to work harmoniously with these natural systems. As our knowledge of precipitation processes continues to advance, we gain deeper appreciation for the elegant complexity of atmospheric systems. The same physical laws that govern individual molecules also control massive weather systems, creating a unity of understanding that spans vastly different scales of space and time. The atmosphere operates as a vast, three-dimensional ocean of air in constant motion, redistributing energy and moisture around the planet through processes that require no conscious control, yet operate with remarkable precision. Within this fluid envelope, precipitation represents the visible manifestation of invisible forces that shape the conditions supporting all terrestrial life. In the quiet moments between storms, when humidity hangs gently in the air and clouds drift peacefully across the sky, we can sense the potential for precipitation that surrounds us constantly. Invisible water vapor fills the atmosphere, carrying within it the promise of future rain. Temperature gradients create subtle air movements that will eventually organize into weather systems. The Earth's rotation slowly influences these movements, setting up circulation patterns that determine where tomorrow's precipitation will form. So when we speak of how rain decides where to fall, we understand now that this is the gentle poetry of physics made visible. There are no conscious choices, no intentions, no deliberations happening in the clouds above us. Instead, there is something far more beautiful: the inevitable unfolding of natural law, operating with such quiet precision that it creates patterns we can predict, rhythms we can count on, and cycles that have sustained life on our planet for billions of years. Every raindrop that touches your skin has completed an extraordinary journey guided entirely by the fundamental forces that govern our universe. Temperature differences create pressure gradients. Pressure gradients generate winds. Winds transport moisture. Cooling air releases its burden of water vapor. Gravity pulls each droplet earthward. These simple, unbreakable rules combine in countless ways to paint the intricate tapestry of precipitation patterns that stretch across our world. In this gentle mathematics of the atmosphere, we find both scientific wonder and profound comfort. The same processes that bring life-giving rain to distant valleys also operate in the air around us right now, preparing tomorrow's weather with the same patient reliability that has characterized Earth's climate throughout its long history. The invisible forces that shape these patterns ask nothing of us except our quiet appreciation for their elegant consistency. As you rest tonight, remember that you are surrounded by this atmospheric symphony, this three-dimensional ocean of air that breathes with the rhythm of seasons, pulses with the energy of distant suns, and carries within it the moisture that will become tomorrow's gentle rain. In its timeless circulation between earth and sky, we find connection to something larger than ourselves, yet as intimate as the air we breathe, as constant as the turning of our planet, as reliable as the dawn that will come again.